Okay, lots of disparate topics today. See how far we get. Okay, so background reading from last week were two industry papers. The Versal paper from Xilinx, Agilex paper from Altera. We've talked about bits of these. We'll talk about some more bits of them in this lecture. Next week reading, so one on, which maybe we'll get started on this week, but basically networks on chips and FPGAs. So what's the case for putting them in? Since this paper was published, they have got into various FPGAs, first Versal, so, and now then Achronix, another FPGA vendor, and in Intel's Agilex M devices too. So this is a paper, the kind of academic paper that looks at the case for networks on chip and how you put them in an FPGA, and since then they have shown up in most of the high-end FPGAs. And then this paper is a bit different. So it's basically on Cerebrus's spatial architecture. So the reason I believe it belongs in this course is this is not an FPGA for sure. You could think of it as, it's an array of processors. So it is spatial computing. It has an embedded low-cost NOC spatial interconnect, and you explicitly move the data around. So it's definitely a form of spatial computing, but it uses vector processors as its fundamental compute elements instead of LUTs. So it's a hybrid device. It also uses wafer scale integration. So it basically is a form of integration that makes much, much bigger chips. So interesting in a couple different ways, but you can think of it as, yeah, combining some FPGA-like, processor-like, and CGRA-like qualities. So we'll talk about that some next week too. And next week is the last lecture. I know that that'll be a sad day, but don't worry. This lecture, you got one more after it. So we'll go through these. Might get some of this today. We'll talk about that next week and a bunch of other things. So, and if there's interest, I think I'll assign one more reading next week, which we won't be able to take up on flash-based FPGAs, but could be interesting. And time permitting, I'll talk a bit about flash-based FPGAs next week too. Yeah. No test next week, just lecture. Test is not for 3 weeks. Okay, so. Okay, so that's readings. Where are we in course concepts? So we're in detailed FPGA architecture, so we're over here. So we talked about routing architecture last week. We're going to talk about some more routing architecture, but it's a little bit of stuff we just didn't get to last week, and then things that are routing but a bit more specialized. Some recent FPGAs have started putting registers in their routing, so we'll look at like, well, how do you do that? What is the case for and against that? Clocking is a form of routing, but needs some special handling, so how do FPGAs do that? And then a lot of systems, and FPGAs were pioneers in this, have started using more than one piece of silicon. So we'll talk about how do interposers work? What are those? How do FPGAs leverage them? And if time permits, we'll get a bit into NOCs too. So we'll see if we get there that far today. Okay, so this is like just kind of finishing off routing architecture, a couple more optimizations we can make to routing architecture before I get into kind of the bulk of today's lecture. So cast your mind back a week, right? We're talking about ways that we can make programmable routing faster and dense, not take too much area. So something that's been done in a few different ways is what I call speed unbalanced routing. Okay, so what does that mean? Well, it basically means don't make all your interconnect the same. And we've already looked at you can have different wire lengths and so on. But you can also make your interconnect different just electrically, like actually make a couple of different electrical design choices. One of them optimized for area, one optimized for speed, and mix them together. So this is a paper that I wrote during my PhD that did that by basically making 20% of the wires faster in a relatively simple routing architecture, and basically doing that electrically. Okay, so there's a bunch of ways you can make wires faster by spending area. So in this particular case, what I did is space them out more. Okay, so they take more area in the metal stack. I basically move their neighbors further away. And that is going to reduce the coupling capacitance to the neighbors, reduces the wire capacitance, makes the wiring faster. So this is showing basically the delay of a bunch of benchmark circuits averaged together. And what happens as I make more of the wiring basically spaced out. So it takes more area, but it gets faster. And it's very nonlinear. Okay, so basically what happens is once I've made 10% of the wires extra fast, the critical path delay has dropped by about 20%. And if I make 20% of the wires faster, it drops a little more. And then after that, it really doesn't move very much. Why do you think this is happening? Does this make sense? What do you think? Did I just make it up? I should take back my PhD? It's too late, right? Well, maybe it's never too late. Actually, you've seen in the US, people can dig up your thesis, look for plagiarized passages even years later if you're in Congress, and go after you. So maybe I shouldn't ask these rhetorical questions. Maybe someone's going to get my thesis and cause me lots of problems. Yeah, what do you think?
I guess that would make sense because at some point, if you make more of your wires faster, the critical path will change. And then something else will be limited. I guess it's possible instead of something else.
So you're saying like basically you've squeezed as much out as you can, right? Because you've used this on the critical path. Is that right? Now something else becomes critical, but maybe that's not using wiring. Maybe it's mostly logic or something. It's not that many wires and there's not much I can do about that. Yeah, and that makes sense. So I take this as a sign that the router, this is inside an early version of VTR or VPR, is pretty good, right? Because if the router was actually just not paying attention to timing, you'd expect this to be kind of linear. Right? If you make half the wiring faster, half the wires on your critical path use it. But we're doing better than that. Like when we make even 10% of the wires faster, we've actually gotten most of the gain we can get. So that means the router's done a good job of finding the timing critical connections, moving them to the fast wires. As we make more and more wires faster, we've just kind of moved all the stuff that's limiting us, all the routing that is limiting our speed has gone onto the fast stuff, and we don't get anything more. So this is actually pretty good news. It means if we have techniques that will cost us some area, maybe bigger transistors, maybe space the wires out, we can actually get most of the speed gain if we only, in this example, put 20%, maybe even 10% of our routing resources use that optimization. The router will actually go and move our critical paths to that, and we get most of the gain. So it's better for us to actually make some things faster and some things slower than to try to make them all kind of average if we're working within a fixed area budget. Does that make sense? Yeah.
I'm wondering, like, I would expect this function to be monotonically decreasing, but it looks like if you make all of the tracks fast, somehow the critical path goes up.
Yeah, that's basically CAD noise. Like, there's no reason why that should happen, but it's also very small. Like that's very close to flat. And the CAD tools are imperfect, right? So when you change the routing, and the CAD tool basically converges to a different solution. And that solution, you're right, should be at least as good, and it's very close, but in this case, it's not quite as good on average. So that's why you do 20 circuits. It kind of makes these effects smaller. If I had 80 circuits, it might be even smaller. So it's a good question. It's also why you kind of want to know what the noise margin of your CAD flow is. And you can do that by for example, in VPR, you can specify a seed, which is a random number to start the optimizers with. If you're finding that changing the seed changes your results by about as much as what you're trying to do, it means you're actually exploring noise. And you kind of just want to stop, right? And say, that's too small. If I need to look for changes that small, then you need to run more benchmarks, or you can actually run multiple seeds and average them together. But yeah, good question, but that is basically an artifact. There are other ways you can make things faster. Okay, this is from the Stratix 2 paper. So we saw that usually the most area efficient, the best combination of area and delay for a routing mux, as long as it's not really small, right? If it only had 4 inputs, you can make it in 1 level of pass transistors. But if it's got 16 inputs, for example, that works well in 2 levels of pass gates, okay? And that's basically what I'm showing here. I think this is actually, what I'm showing here is a 9-to-1 mux, which is a little bit smaller. But basically it's 2 levels of muxing. This is like my first level of muxing, and then these are my second level of muxing. And we saw how to build 2-level muxes like this. And because we can share SRAM cells on the first level, they're pretty area efficient. What this paper does is it says, well, I mean, going through 2 pass transistors in series, which is what I have to do, okay? So this is like a routing wire. right? And if I want this routing wire to connect to the output of this routing mux, I turn on that pass gate, and then I turn on that pass gate, and then I go through these inverters and I go out. So I got 2 pass gates in series. And it would be expensive. I could redesign this with a whole bunch more SRAM cells, and I could make it so there's only 1 pass gate in series for every routing wire, but we already saw that it took a bunch more area, so I'd rather not do that. So what this paper does is it says, well, let's just take 1 routing wire here, call it a fast input, and it's going to go through 1 pass gate. Okay, so this mux is now unbalanced, right? It's mostly 2 levels, but there is this one special input that only gets 1 pass transistor to go to the output. Okay, so it's a mixed depth mux. And the purpose of that is to give us, some extra fast inputs, right? And maybe the CAD tools can make use of that. And what they found in this paper is that actually making 1 fast input gets about 4 to 5% more speed. So the CAD tools were able to use this fast input quite a bit, which again means that they're pretty good. They're pretty good at finding the critical paths of the circuit and giving them priority when they're looking for routing resources. This paper also looked at, we could do 2, fast inputs, but it's getting more expensive. Like in the limit, we make all inputs fast, but that means we got a 1-level mux, and all our routing muxes got more expensive. They found that, making more fast inputs than this increased area, but it got diminishing returns. Wasn't really a good idea. So similar idea, right? Try to make yourself some fast paths. You don't have to make everything fast. Do you think this will combine with the previous idea of making wider metal spacing? So what do you think? It's like a 50-50. So again, if you've been waiting for your chance, you got 2 lectures left to say something, and you got a 50-50. It's not going to get much better than this. I don't know how to craft a question that has 2/3 probability of you being correct. So, yeah.
I guess the issue with having more wider metals, like if you want wider metal spacing, if we're crossing POC
Yeah.
you're probably not going to be able to do that too well.
So you think it'll just be hard to fit in?
Yeah,
Yeah.
it feels like 2 competing objectives here. One is to make something wider, but then also have more gears down all the way to the
Yeah, so it could be hard to, each of these takes some complexity in layout, so you're right. It could be a complicated layout, so maybe that gets hard to make. Anything else that might concern you, right? So, there's no perfect, this is one of those questions where actually the answer is kind of maybe. So if you wanted better than 50-50, this is probably it, right? So it could combine. What will generally happen though is there's some point where you start stacking up. I got 1 out of every 10 inputs is fast, 1 out of every 5 wires is extra quick, and I start stacking all these things together. Eventually you do make it too hard for the router, right? You will get diminishing returns because the router is like, I'm trying to use 1 of the 10 fast inputs, and I'm trying to use 1 of the 5 fast wires. There's a point at which it won't fall off a cliff. It's just you won't find that just making 10 or 20% of things fast is enough to get most of the gain, because they're starting to conflict basically. Like the router's not infinitely good at trying to move everything together. And it might not even, unless you're clever about it, you might find that the 20% of wires that you made extra fast don't quite line up with the 10% of inputs that you made extra fast, and so on. So, yeah, was there, yeah.
So what if we just make the fast input and only the fast input?
Well, okay, so how are you doing that? Are you just going to delete the rest of the mux?
No, I mean
Because you could do that, so that's a valid design choice. Let's say you did that. This fast input will be quite fast. I even got rid of some extra loading here, so it got even faster. So maybe this is like super good. What do you think? Yeah, I mean, the problem is that I did just make this mux super small. I mean, this is kind of insane. I actually made it a 1 mux, so that probably is maybe a sign this might be infringed too far, because I could just take the pass gate out and say I just wired this to that. So one of the ways to interpret your question is, could I just reduce the overall size of the mux? And you could, and it'll get faster, but this is where you're getting into how far can you push it before your routing flexibility is too low, your channel width explodes, et cetera. So you're in that whole complicated optimization space. If you've decided that 10 inputs works well for routability, this electrically you can say, well, I'm going to make 1 of them extra fast. And I will pay maybe a little bit of area for that. I mean, in this particular case, maybe I wouldn't, because I don't know how I make a 2-level 10-to-1 mux, but I could have made a 12-to-1 mux, for example. I decide not to do that. I'll make it 10 and make one of the inputs fast. I guess the other way I can interpret your question is to make them all fast. What's making these slower is the fact that I have to go through 2 levels of mux. So I could say, well, don't do that. Okay, restructure this whole thing to basically be like this. One ASRAM cell controls one pass gate, because I could just keep repeating that. Right? I could do that again down here. Maybe I can't draw very well, but you get the idea. But what I've done is I've converted back to a 1-level mux. It does tend to be faster, but it chews up a bunch more area. Does that make sense?
What if we make the cascade forward path with the cascade forward?
Yeah, and actually, that I can't actually remember, but that might have been done too, because that's another thing you could do. Yeah, why not make it extra big too? So after you've kind of decided on a good routing topology, you can play these tricks of basically going, well, now instead of making everything the same electrically, maybe I'll make some of this, I'll make a fraction of it extra fast. And basically, good CAD tools tend to like that. They're pretty good at finding the critical path and moving it to your fast stuff. But not infinitely good, okay? If you make, like, I have 100 different ways I can make 1% of the stuff extra fast. This is going to be a needle in the haystack, and the CAD tools aren't going to be able to move it all to the fast stuff. Okay. Okay, so that's it for kind of conventional routing architectures. The next thing I was going to talk about is registered routing. I told you, like, whenever you see like multiple major FPGA vendors do something, you know it's probably here to stay. So this is one where there's no general agreement still. Okay, this is a big change that Altera did in the Stratix 10 generation to not just have registers in the logic blocks anymore. They put tons of registers in the routing. And then Altera's been changing this, you know, kind of chip by chip. You'll see Agilex is a little different, and Xilinx has also been responding, but in different ways. So this is a place where I'd say there's no convergence of, like, what should you do? There's a whole bunch of different answers. Hopefully, how many people read this paper, actually? Because you don't have to read all the papers, although it's a good idea since I might ask questions for them. Okay. I think it's an interesting paper. I encourage you to read the papers, even if you don't have the energy to fill out the questionnaires for all of them. Yeah?
So I have a question. Like, you submit a paper titled the Stratix 10 architecture. How do you double blind?
You're saying, like, you think it's like some academic research group that just stole Altera's trademark? Yeah, I mean, the authors are double-blinded. Obviously, people who are reviewing it can guess, like, who did it, although not always. I remember the paper that actually introduced floating point DSP blocks to FPGAs, and it was almost rejected from the conference. I wasn't a reviewer on it, and I had left Altera by this point, so I wasn't actually a conflict. But at the program committee meeting, I was like, I think, let me read this quickly. And I was like, this is a pretty interesting paper, and it's going to have big impact. The reviewer who was most negative on it did not actually realize that it was actually implemented in a chip, because the comments were largely like, no one's going to do this, and it was like, they're going to sell this, right? So sometimes, like, sometimes it's more blind than you would think, right? So. But yeah, generally you kind of can guess a company did this, and double blind is not, if you try to pierce through it, you often can. You're just not supposed to try to figure out who the authors are. Okay, so what's the motivation for this change of putting registers inside the interconnect? Okay, so designs have become more and more register rich in FPGAs, and the chips are physically large. They depends. If you have a small FPGA, it may not be that big. But mid-size and especially high-end, big, expensive FPGAs, the biggest FPGAs tend to be, some of them are actually at the reticle limit, 800 square millimeters. Commonly, the biggest one in a family is maybe a bit smaller, like 500 square millimeters. But those are big chips. And to get across the entire chip, even you design your routing architecture as well as you can. You have put in some long wires. You actually increase the metal spacing. You put big routing drivers on them, etc. It still takes many clock cycles to get across the chip, okay? And what that means is that you actually have, it's common in designs that are trying to push clock speed to actually have paths with no logic in them, right? You'll just have a register driving a wire, driving another wire, driving a register, and repeat that maybe 5 times or 10 times or even more to get all the way across the chip. You hope you don't have too many paths like this, like the placement tool actually managed to localize the logic, but you usually do get some things that do actually have to cross the chip. And yeah, it's all wiring, but you have to put registers in it. The delay to get in and out of the logic block, basically, you could use a logic block to pipeline this. So you can say logic block register, wire, wire, another logic block register. But that means you have to get into the logic block, to the register, come back out of the logic block. And that has some delay, right? We have that connection block input mux. We have a local routing inside the logic block. Then we have the flip-flop delay. Well, we have a delay to get to the storage node of the flip-flop, which is basically called TSU. So that's on the end of one timing path. And then the start of the next timing path, we have the delay to get out of the register storage node, which is usually called TCQ. And then we have to get possibly through some local interconnect and then basically back into the programmable routing with like the routing driver. So that delay to get out of the, get off the regular routing and get basically into the logic block through its local interconnect and then do the same thing coming out of the flip-flop it adds up to about 300 picoseconds I checked this in 28 nanometers. So that'll scale. So in a 10 nanometer chip, it's going to be somewhat lower than that, but everything else is faster too. So it's a noticeable fraction of your clock period, and it's generally more than equal to like 1 or 2 or 3 of your regular routing wire delays. So it's not the end of the world, but it basically means if I want to pipeline this path, this is not fast enough, I need to put a register in here, I'm not going to get quite as much benefit from the pipelining as I'd hoped, because I'm actually going to first have to take this 300 picosecond delay hit, and then I'll cut the remaining delay in half, like into 2 clock periods. So could we do better if we had registers right on the routing wires so that we get rid of this 300 picoseconds cost, and we could have like lots of registers now directly in the routing. But this is only going to be useful if we can do it with low cost and we want the registers to be fast. Okay, so that's the upside. The downside is these registers in the routing are going to be harder to use. We're going to waste a lot of them. Why are we going to waste a lot of these registers compared to the registers we put in the logic block? What do you think?
I guess because if you're not using that wire, or if you have a flexible combination, you have more use of these registers. It's very hard to use all the routing paths.
Yeah, so exactly. We never use all our routing wires to begin with. We're not going to use them all as registers. If we don't use this particular routing wire and want to register exactly there, well, nobody else could use that register, right? Whereas the logic block registers, essentially these are like 2 sides of the same coin. They have muxes so that we can reuse them in different ways. On the other hand, those muxes, that local interconnect costs us delay. So we're trying to get rid of that. We don't need that local interconnect to get to the register anymore. Part of our cost is going to be that makes the registers fundamentally more limited in their use. We don't use it right on that wire, it's going to get wasted. It's going to make the CAD flow and the architecture more complicated. So this is actually a really big change. I've had friends at Altera who told me that if they had known how hard this would be in the production tools, they probably wouldn't have done it. Now they did it, so they've amortized all the costs, but it took years to get the CAD tools into the shape that they wanted to fully explore this. That's a sunk cost. I mean, they've done it now. There's an area overhead. Okay, these registers are not going to be free, and it's going to be a lot of them if we put them in the routing. We are going to slow our routing switches down. So you're going to see how electrically Altera did this, but basically adding a register inside the routing switch, it's going to add some delay, no matter how you do it. At least adds load, maybe it adds some extra transistors on the signal path. In this Stratix 10 paper, they mostly don't talk about that. They say it's small, and I'm sure it is small, but they kind of don't give any numbers of exactly how much they slowed down the routing switch. And then another question you have is you can put registers in the routing. How do we get the clock to them? So we don't know what clock they'll take. And we're going to see this later in this lecture. FPGA spent a fair amount of effort to get the clocks, let you control the clocks, get them to the right spot. We're going to have to be pretty careful that we don't add a lot of programmable routing and programmable muxing to get these clocks to all these registers in the routing, or that's going to be extremely expensive. We already spend a bunch of area to get that to the logic blocks. There's going to be way more registers in the routing, so we're going to have to make sure we're very efficient about how we get the clocks to them. And we probably can't just say, well, they all use one clock, right? Because FPGA designs don't all use one clock. So that would be cheap, but it's probably not practical. So the very clever trick that Stratix 10 uses is they don't actually build, part of how they make this cheap enough is they don't actually build registers in the routing. They build what are called pulse latches. Okay, so this is your standard design for a register. So you've got two latches, okay, so cross-coupled inverters. And so this can now hold its state. Okay, it's just like the cross-coupled inverters in an SRAM. But I basically make this, there are a bunch of ways to make this, but one way I can make it is I can make this inverter a tri-state, and I can make this input inverter a tri-state. And now when the clock is low, basically if the clock is low, I'm going to just hold my previous value, okay? That path is enabled. When the clock goes high, then this path is broken, okay? Well, it's broken through there. And this path is enabled, so I basically copy in new data, okay? So right when the clock goes high, new data makes it in. But this one, let's see if this is all correct. Okay, when the clock goes, I might need an inverter here. Okay, I think this should be clock goes.
No, it's right. The first clock is inverted.
Oh, it's clock bar. Okay, yeah, thank you. Okay, I was looking at that going, wait a second, I can't repeat the same thing twice. I missed the bar. Okay, so now when the clock is high, okay, so when clock is low, let me think about this again. Okay, when clock is low, I make it into this storage node, okay? And then when clock, so clock is low, I make it into the storage node. When clock goes high, I hold it, okay? So here's where I make it to the first storage node into 1 while the clock is low. And then when the clock goes high, I basically allow it through the second storage node, and it'll actually go out to the rest of the circuit. Okay, so it's basically edge triggered. You see the data come through right when the clock switches to high, because that's where the data flows through out of here. And we're holding whatever the data was when the clock went high here. Okay, so that's how we build our regular register. Okay, so what does a pulse latch do? So a pulse latch doesn't actually have two latches. It only has one latch. How many people have heard of a pulse latch? Do you know, have you ever heard of this in the class before? Okay, so a couple of people have heard of it, 3 people. So yeah, pulse latch only has one latch, but it behaves a lot like a register. Why does it behave a lot like a register? Basically, this clock pulse, notice that is not clock. That's CP, which means clock pulse. So when I had my clock, it looked like this, regular clock. And it was on this rising edge that my data flowed through. I can build a little circuit, and I'm going to show you what Stratix 10 builds on the next slide, that basically turns clock edges into pulses. So this is what CP would look like. Okay, so I have a train of pulses where there's a short pulse. Short meaning, usually low hundreds of picoseconds. And what happens now is when this clock pulse is high, my data flows through the latch, okay? And as soon as the clock pulse goes low, this is cut off, no new data comes in, and this latch is turned on, I hold the data. If this pulse was infinitely small, and it was right at the rising edge of a clock, this behaves exactly the same way as an edge-triggered flip-flop, okay? Now, in practice, I can't make this infinitely narrow because it does take some time for the data to get through here and get safely stored in this cross-coupled inverters. Like if I actually try to make that pulse 1 picosecond wide, basically I won't actually properly charge the internal nodes and I just won't capture the data. Okay, so there is a minimum pulse here that is a function of essentially all the delays inside of here. You've got to make your pulse at least that long. Okay, but what's nice about this? Well, there's just one latch, so it's actually smaller. So it's a good way to make a very cheap register, because I got rid of basically half my transistors. Let me erase all this stuff. I guess I just mentioned all of this. So it behaves actually like a fast register, because when you analyze a register, you wind up with a few important parameters that you can write on the register. So one is TSU. Quartus calls this, you'll see this in the time reports, Quartus calls this micro TSU. So it's basically the setup time, like how far in advance of the clock edge does the data have to arrive to be safely captured in the register. And you'll see another parameter called micro TC, I think Quartus calls it micro TCQ. So that's the delay from the clock to the output. So when the clock arrives, how long before the data comes out, okay? Whereas this TSU is how far in advance of the clock do I need the data to arrive so that I can safely capture it? Basically, the sum of these two things will be the delay through these two latches. Like you can divide them up in different ways, but basically you need to make it through this whole structure, and that will be, if you spice all this, that will turn out to be these two numbers together. And those two numbers show up in your timing reports. This is the delay, this micro TCQ is at the start of all your timing paths, and the micro TSU is at the end of all your timing paths. So you basically always get one of each on any path that is limiting your clock frequency. And basically, you can calculate them as the sum of the delay through this. Or they're at least very close to that sum. So this basically has less delay. So it will have a smaller micro TSU plus micro TCQ, okay? Because of the fact that there's just one latch in series. So it's actually a very fast register. Yeah?
So is there a difference between this and the setup and hold time?
This is all setup, okay? So micro TSU is something that will go in your setup time analysis. Micro TCQ will also go in your setup time analysis. I'm going to show an example later in the lecture because I think it's actually pretty important to understand hold time and setup time, and actually ask it on the qualifying exam, and tons of students don't really understand it. How many people here think they really understand how to analyze setup and hold time in a circuit? Okay, so a reasonable number. How many people are like, no, I do not ask me that in the qualifying exam? So, okay, a few. And now you add this game within a game of, should I say that, right? Like if I say that, is that for sure what he's going to ask me? So you'll find out in a year. So anyway, basically, I'm going to show you how to do a setup time analysis later in the lecture, I guess. But both of these will show up in your setup time analysis. Your setup time is essentially your long path cannot go faster than this. Hold time is different, which I'll also show you that. Does that make sense? Yeah.
To me, poor hold time implies that, so I might go back to understand hold time analysis as well. To me, it implies that we actually have to hold the data long.
Yeah, that's exactly what poor hold time means.
Poor hold time means you have to hold the data long.
Yeah.
But to me, if there's a clock pulse, I don't know how it would force you to hold the data long.
So I'll draw this out in a minute, and hopefully that'll make it more clear, okay? Basically, yeah, it's essentially your hold time. Yeah, I think it's probably best if I draw this out. What hold time is getting, okay, what setup time is my data gets there in one clock period. Okay, I have no paths that are longer than a clock period, because then my data doesn't make it to the next set of registers in a clock period. Your hold time is my data must not make it there in 0 clock periods, okay? Like I can't get data from the current clock edge just flowing through some downstream registers, because that breaks all my logic, right? Like nobody makes a finite state machine where it goes, maybe my state changes twice in one clock period, which is effectively what would happen if you have a hold time violation. So I'll try to draw this out in a minute, but effectively, like let's say I make this pulse long, okay? Like it turns out that to guarantee that I've captured the data, I need to make this, that's maybe too long, it looks like a whole clock. But I would like to have a really short pulse. Maybe that turns out to be unreliable, I have to make it somewhat wider. During this whole period where the pulse is high, data will flow through that latch. So you can imagine like how that means if data arrives, the clock edge is here, okay? And data starts flowing, my through my latches, through my registers to downstream logic. If some of it makes it to a downstream register before this edge goes down, it actually makes it through that latch. So the wider this edge is, essentially the worse your hold time is. You got to make sure nothing gets there during that pulse.
So it's really a function of how short you can.
Yeah, it's a function of how short you can make your pulse. If you can make the pulse infinitely short, then this would have great hold time, but you can't. Does that make sense?
Yeah, no, that makes sense. I kind of completely blank that this is a latch, so data's one.
Yeah. Okay, so we've got a fast register, it's a cheap register, but it has, because we can't make this pulse infinitely narrow, it has this kind of bad behavior. Okay, so how do we make this pulse? So we make what's called a, well, you make a pulse generator, okay? That's what this is. So this pulse generator is, I have a clock, it comes in, I make a delayed version of the clock. Making a delayed version of the clock is easy. Okay, so FPGAs actually use this thing called a delay chain over and over again. So I think I already showed you this a couple times. That's what this is. So this is a whole bunch of, actually let's make it like this. Okay, so make an inverter chain. And basically I can take various points along this inverter chain that are the non-inverted points and send them all into a mux. And that's what I'm doing here. Okay, and that's my delayed clock. Whoops. Okay, so that's my delayed clock. Okay, I think I'm going to stop drawing on the slides and draw on the board. Microsoft is trying to tell me something. I'll try once more without pushing on whatever magic thing. It's impossible. Okay. Okay, so let me just draw this here then. If I can find a chalk. Okay, so I build this delay chain out of inverters. Okay, and I can control this with some SRAM cells. Okay, so that's another very important FPGA building block of a delay chain. And it's programmable. You just program things in. I might take very little delay, or I might take 2 inverters, or I might take 4 inverters. Okay, so that's what this delay actually means here. And the logic here is basically I'm just taking the AND, well, the AND between a clock. Okay, so I've got a clock coming in here. And then I'm basically making a delayed version of the clock. And I can choose how much to delay it. So I can delay it, maybe I choose this point. Okay, so I program in SRAM cells that are maybe that's 1, 0. I select that point. And that gives me a clock delay that is, let me draw this a bit better. Maybe I shifted that much. So I get a delayed clock here. And if you look at this diagram, they're basically taking the delayed clock, inverting it, and ending it with the other clock. Okay, so if I take the delayed clock and invert it and end these two things, let's see, so I take the original clock and the inverted clock. I probably should have drawn this out in advance.
They invert the delayed clock.
Yeah, which one did they invert? They invert the delayed clock, right? Okay, so I invert the delayed clock. I'm going to get this plus this. I'm going to get this piece, right? So right there. So in my head, I'm inverting this, right? And then ANDing it together. And what I'll get is basically a pulse here. okay? And a pulse here, and so on. Okay, so this does what we wanted it to do. It basically made a chain of pulses where every pulse is by the rising edge of our original clock, and the width of the pulse is configurable by these SRAM cells. Does that make sense? This circuit, this is not a really expensive circuit, but they're trying to keep this whole thing cheap, right? The whole idea of a pulse latch was it's cheaper than a register. So we don't want to build one of these for every single register. So Altera they basically build this once in a while, essentially. You'll see the details of that later, but they have to share this across a whole bunch of registers to make this cheap enough. Does that make sense? Okay. Okay, so I already said that. They want to share this clock generator, pulse generator to amortize its clock. So that's going to be an architecture question. Basically, if I share a clock pulse generator, it means I have to share the same clock. It also means I'm sharing the same pulse width. So they'll have to be careful when they share this. They couldn't say, let's just share it across every register in the whole device, because that kind of means we only have one clock. And that's probably not good enough. But if they say every single pulse latch gets its own version of this, that's too expensive. They would have been better off just building like registers everywhere. So they're going to try to amortize it as much as they can. I already talked about this. To make the pulse width configurable, well, okay, why do you think they make the pulse width configurable? So why, like, we could just basically say, let's make 2 inverters or 4 inverters. Why am I building like 6 or 8 inverters in this mux? Let's say this is 8 inverters in this mux and these 2 SRAM cells. I mean, that's more expensive than just building 8 inverters. So why didn't I just build 8 inverters? Yeah.
I guess in some applications you may really care about power versus primary objective.
Well, this won't gate the clock. No matter how many inverters I go through, like whether I go to 2 or 4, it's only going to affect my pulse width. But I'm going to get 1 pulse for every rising edge. So it won't save me power. Well, I mean, I guess if I only built 2 inverters, it would save me power versus 8. But I won't get rid of any pulses. Does that make sense? So it's not primarily for power. So yeah, so I would ideally, yeah, maybe that's the right way to think about it. Like it's this trade-off. So is there a trade-off here? So what do you think, Robert? Any ideas? Or?
Yeah, could it be trying to match with the data?
Let's see. I guess basically what I'm trying to do is make this thing behave like a register. So the narrowest pulse I can get is kind of the best for making it look like a register, because it gives it the best hold time. So if I really want to have a good hold time, I should just make this pulse width really small. There is making the pulse width longer. It can allow what's called time borrowing. Okay, time borrowing means the data actually can be captured a bit late in the clock cycle. So it actually can be used to optimize the design at the expense of making your hold time worse. So Altera's CAD tools can actually analyze that. So you're right, sometimes making a clock pulse a bit wider essentially allows the data to arrive a little bit late, but you have to be really careful doing that you didn't unintentionally create a hold time violation. But yeah, that can be a factor. It's not the main reason they did this though. Yeah.
Is it because of process like variation within the flip-flops? Some may have longer hold time, shorter hold time. You want to account for different flip-flops in your process?
Yeah, that's exactly why. That is the fundamental reason why this was done. So let's say you put in, okay, you would like this pulse to be short to get a good hold time. So you could say I need 2 inverters and I got a great hold time. If it comes back and there's a bit more process variation than you expected, your inverters are a bit faster in some registers than you thought, your pulse latch is a bit slower, your chip doesn't work. Okay, and maybe no chips. All you need is 1 register to not work that you have to throw it away. Well, I guess in Altera you need more than a few rows to not work. But so that might have been like a super embarrassing decision where you say, I was sure it was going to be 2 inverters, but it turns out no. So you could be now really conservative. Say, look, I'm going to put 16 inverters in. My pulse width is going to be 500 picoseconds. But that means all your pulse latches are kind of bad. You have hold time problems all over the place. And maybe it turns out that actually, you could have gotten away with a 100 picosecond pulse. So this is something that FPGA architects do quite a bit. because you have a whole CAD system that can program stuff, if you're not quite sure, and often for things like this where it's a function of process variation and complicated differential kind of timing between this and that, you'll put some extra configurability in just as a security blanket. And I know actually that they wound up in Stratix 10 having to use bigger delays than they wanted. Okay, not bigger than they built, but bigger than they ideally would have wanted, because they said this in the Agilex paper. So part of this is not secret, they just told you. So there was actually more variation than expected, and it was actually important that they had these programmable delay chains so that they could adapt to that. And they do the same thing in RAMs, for example. I told you in RAMs there's all these self-timed circuits. The clock edge arrives and you start pre-charge and then you turn on the sense amps and so on. All of those have some configurability too, so the Quartus CAD system, after a bunch of chips have come back, you can actually decide what settings to program into all those things, and it makes your RAMs essentially more robust. Yeah?
So, is that configuration like done by the configuration bitstream, or is it done like the alter builds the chip, looks at it, like what's the actual value, fixes this, and like that's it?
No, it's done by Quartus. So it is the configuration bitstream, but Quartus is told, the engineers who are doing this in Quartus are told what the characterization data is showing. And what they'll know is basically the speed bin of this, like the speed grade of this chip. And then they'll have to program settings that guarantee that any chip that has that speed grade will work. Does that make sense? So it doesn't have to work for every chip, because chips, FPGAs are speed binned. But any chip that would go in the speed bin, basically the product engineering team will measure a whole pile of chips, figuring out, do they work with these settings, do they work with that settings, and basically feed that to the software team to say, don't use these settings. And they can even change their mind, right? Like if you make you later on the process distribution drifts, you could even change the CAD tool. Yeah?
I guess outside of time boring, does it ever make sense to the clock pulse drift on?
No, it's what it only is good for, it does allow time borrowing, but that's pretty complicated, and it makes your pulse not collapse. Other than that, there's no reason you'd actually like to be short. Does that make sense? So, let's see. Okay. Maybe I should draw, we're kind of talking about, yeah, maybe I'll do that in another one. I'm going to draw like a timing diagram at some point to make sure everybody gets this. Let's see. Yeah, okay, I'll wait another couple slides. Okay, so what did they do? So this is basically the circuitry they added. So this is they're using direct drive routing. So they have this MUX, it's built out of pass gates. And everything that's black is stuff that was there before. So they got a MUX, they've got an inverter. This one will be reasonably small. Then they've got a big inverter because it's driving a routing wire. So all of that was there before. What they add is basically shown in the dashed lines. Okay, so they basically add 8 transistors here that are a latch. So this is basically, if you go through it, that's a latch. They also have to make the data input into the latch tri-statable. If you saw my latch diagram before, we had a latch, and part of the latch is the fact that its input can be turned off, so it just holds its state. So they have to take this inverter and turn it into a tri-state. And that's what they've done by adding these 2 extra transistors. This goes from a simple inverter to a tri-state inverter. And it's controlled by these latch enable signals. And they have to build a bit of logic for that latch enable signal. So you can go through the logic of this on your own time. Trust me, it works, but I'm surprisingly bad at following through simple logic gates on the board. But basically they have an SRAM cell, which if they program a 1 in this SRAM cell, this latch enable will be 0, right? And the end latch enable will be 1. If they don't program that, basically the latch enable will be 1 only when the clock pulse hits it. Okay, so they can turn the whole thing off, and this acts like a regular routing driver. These just basically, that's a 1, that's a 0. Or if you set RCOM to 0, basically this will be tied to the clock pulse, and it'll act as a latch. They also have a little inverter they have to add here. This is that weak pull-up, like that keeper. So you need a pull-up transistor. We were normally just connecting it here. If you remember the things we drew on the blackboard, because you've already got an inverter. Because this inverter now, they've turned it into, this whole thing into a latch, they can't guarantee that this node is actually the inverse of this node, because it might just be cut off, and it's holding some data. So they have to build a separate inverter. So there's another extra 2 transistors. So in the paper, they say they have to add 10 transistors, which basically are all these ones in the dashed lines. Most of them are small, okay? So 8 of them are the minimum size, 2 of them are somewhat bigger. I'm guessing it's probably these 2 that are bigger. And they say in the original multiplexer plus drive circuitry, they had 73 transistors, and many of them were big. For example, these 2 transistors are going to be quite big. They're driving like an entire routing wire. So they say that that adds up to a 5% increase in the logic block area. So the whole LUTs plus routing, et cetera, got 5% bigger, although they leave out something that they never talk about. So there's this, they have this, right? They still need this SRAM cell and this little bit of control circuitry to build these latch enable signals. And they're also going to have to add, you're going to see in another couple of slides, they have to add things for the clocking. They never say what the area of that is. So you can't quite tell how much area they added. It's more than 5%, but you can't say how much. But I guess it is very clever, though. I would say this architecture's, yeah, it's got a lot of nice features, and they've been able to add register. This is much cheaper than a register. It's not adding much delay to the signal path. The delay it's added to the signal path is just a little bit of load here, and the fact that this inverter turned into a tri-state, which is a bit slower. But it doesn't slow down your routing driver very much, and it's not very big. So it's pretty clever. Okay, so that got me my registers, and I have tons of them now, right? So the start point of every single wire has an optional pulse latch in it. How do I get clocks to all of those things? So what they do is they basically force them to share clocks. They don't want to say the whole chip uses one clock, because that's not going to work with their customer base. And in the paper, they have a bunch of studies of this. We'll talk about clocking later in this lecture, but basically the kind of last stage of getting your clock to your logic blocks are what are called row clocks in Altera devices. And they've got 6 of those, basically going in a row past a row of logic blocks. So there are 6 of these possible clock sources. And what they do is they basically have a MUX network where they basically say, we can choose, we're going to have 4 MUXes, okay? And we can pick one of these 6 clocks that are flying by to be the output of that MUX, and we got 4 sets of those. And then they allow every routing driver, which they call a driver input MUX, to basically pick between 2 of them, okay? So they basically do 2 levels of MUXing. I can pick for each of these MUXes one of the 6 clocks, and then every single routing driver gets to pick between 2 choices, okay? So they, in a sense, every routing driver can pick, well, groups of 50 routing drivers, basically, will have to share the same 2 out of 6 clocks, and then each of them can pick whichever one they want between those 2. And they found that choice basically kept this multiplexing network reasonably low cost, but was still flexible enough that they could get the clocks where they need. And I told you that FPGA designs can have 100 clocks, but they don't have 100 clocks in a really local region usually. They're spread out over the chip. So they found this muxing structure was okay, right? They're forcing, they force some sharing, but not complete sharing of the clock. Does that make sense? Okay, and then they also need clocks. They basically also put these pulse latches at basically right here. Okay, so let me show you what these things are. So a driver input MUX is a routing switch, okay? So this is just Altera's notation. They name MUXes after where they're going, okay? They also have what we would call an input connection block. So the MUX that goes into a logic block input, they call a lab input MUX, or a lib. And this is going to drive a local interconnect inside of the logic block. And this routing driver also includes a pulse latch, okay? So that's also got a register in it. They can register basically the local interconnect lines. And for those ones, they make the clocking a little bit less flexible. They say, we got these 6 clocks flying by. We got one MUX that can pick one of those 6 clocks, and all 52 inputs to the lab have to, if they want to use their pulse latch, they must use that clock. Okay, so they get to pick one of the 6 clocks flying by, but then every single logic block, local interconnect, like input, has to use it. That's a little bit less flexible than the regular routing, where we basically got to pick between 2. So every routing box has a choice of 2. Here you have a choice of 1. Does it make sense that this is a little bit less flexible? Or does that seem random? Yeah.
Makes sense because most likely the entire logic block will be using the same clock as well.
Yeah. So that's exactly the rationale. All of these signals are going into this logic block. Okay. The logic block might use 2 clocks, but usually it uses just 1. And even if it did use 2 clocks, you could say, well, then you don't get to register both of them in the pulse latches. That's not too big a constraint. For the routing wires out here, some of them might be being driven by this logic block, but some of them might be driven by logic blocks halfway across the chip. So you'd expect there's a more diversity in what clock domain it is on, because some of them are just kind of passing through. So the architecture makes sense. In this paper, they have this chart that shows how much speed improvement do they get from these pulse latches in the routing as a function of how big the hold time is. Okay, so the best result is when hold time, what this means is essentially what Cordis would call the micro t-hold of the register. Let's see if I can, I don't know why I can't draw on this anymore. Okay. You think that'll work? Nope, it's impossible. Okay, I will not draw on it anymore. Okay, Cordis calls this the micro t-hold. You might have seen it in your timing reports. This is basically like just the register's hold time. It's essentially, if you look at the register input port, like D input versus its clock, how long do you have to hold the data after the clock arrives at the register? So a really good register has a hold time of 0, right? They can arrive at the same time and the register will properly stop the new data from going through. A bad register out here, this one has 500 picoseconds. Okay, so after the clock arrives, I still have to hold the data stable for 500 picoseconds. As the hold time of the register gets worse, which basically means the pulse width is getting wider, right? They have to be more careful about using these pulse latches. Like they can't use a pulse latch on one wire and then immediately you use it on the wire that feeds because there's not enough delay, right? There's a chance now that the data will flow through both registers in one clock cycle. So they have to get more conservative about using them. So as the hold time gets worse, the gains from this architecture idea go down. And I mean, probably the reason why this figures in the paper is this is something that the architects were worried about. So they're like doing sweeps of like how bad does this get with hold time. Does that make sense? Okay, I think maybe this is where I'll stop and draw a timing picture. Okay, so get that. Okay, so for a bunch of things we're talking about today, you really have to understand timing analysis. So let's see if I can do an example here. So let's say I've got a register here, and it's trying to, I'm trying to communicate with something that's far away on the chip. So I'm going to go through a wire, and then there's going to be a routing driver, okay, and another wire, and so on. So I have multiple wires like this, and I hit another register. And my design is fast enough that this is limiting my performance. So I'd actually like to pipeline it more. So I'd like to basically turn on this register and that routing driver. Okay, so I want to pipeline deeper. And this is all just interconnect, right? So back here, maybe there was a lookup table, but all of this is just interconnect. So yeah, in Stratix 10, I didn't have to go into the logic block and waste a register. I didn't have to add any extra delay, et cetera, to get into the logic block, so it all looks pretty good. But let's say that I also have, in my original design, I have another signal and it goes here, and it only needed a couple of relatively short wires to get there. And when I pipeline, I basically have to, if these are, these are my inputs, and these are my outputs, to have a proper pipelining, I can't just pipeline this wire. I have to find like a cut, right? I have to change the latency of everything. So I have to pipeline this too. So I put a register there. And I didn't really want to do that. Like, I didn't need to do that because this was pretty close. But I did it because I need to keep correctness. So this is where I have to start worrying about hold time. So on this path, let's call this A, and this is B. So on that path, I had a clock here. Well, here's my clock, say. And I make some clock pulses. So my clock pulses look like this. And here is my data here. Okay, so let's say, so at A, from A, I change my data. So it starts to change here, and it arrives at, let's say this is where A starts to change, and basically at B, I get my new data here. Okay, so this is probably confusing on this later, that whole thing is B. So it's changing well ahead of the clock period, it's fine, right? So does this make sense, right? So my data got there before the clock edge. That's my setup constraint. So from this clock edge, the data has to be there before the next clock edge, which is there. And it did that, so I'm okay, right? With the clock pulse, basically the data has to be there before the latch goes opaque, okay? So I have to make sure that that's my setup constraint. My total data delay from A to B cannot exceed, in a regular register, the delay from that edge to that edge, and on this one, from there to when the pulse goes opaque, or the latch goes opaque. Okay, so let's say this is D, and this is C. Okay, so C, like basically I look at signal D. This register starts launching data. Sorry, I should make that D. So this register starts launching data, and it's really short, right, to go from here to here. So the data starts to change right after the clock period, clock edge, and it actually manages to stabilize, like it actually changes before the pulse goes opaque, okay? So your hold time is always a constraint of basically from the launching edge to the same clock period, the edge at the other register, okay? So this is like the clock at C, and this is the clock pulse now, we'll say at D. I have to make sure that I can't get my data basically so fast that it makes it to this register D before the clock pulse has gone low, okay? Because my data is run through. I've made it through in one cycle. Does that make sense? I don't know if I drew this the best way. I think I didn't. But that is your hold time constraint. It's always data getting there in the same clock cycle. So if this clock pulse is reasonably wide, then I have a risk that I made it to D before the clock edge hits here, data starts flowing out, I make it here before the clock pulse has gone low in the same cycle. If that can happen, and that would happen if, essentially that would be represented as a larger T-hold. This is basically my micro T-hold. How I have to add that into my hold time analysis. Does that make sense? So probably the best way to think about it is just to say data launches at this rising edge. There is a wire delay here. Okay, so there's basic, and then there's when does the clock pulse go low? And that, I can't get there before that clock pulse goes low. If that can happen, then this is forbidden. Okay, I can't use that pulse register because it's not working, right? I have a hold time violation. The data is actually running through it in the same clock period. Does that make sense? Yeah.
And in that case, just go around and find another register.
So what you could do is basically say, I mean, it's now awkward, right? A person pipelined, this person say has pipelined his design or her design. They put a register here, they put a register there. So yeah, what Cordis would have to do is say, don't use an interconnect register. That's one option. Actually go into the logic block, use a regular register. Okay, so, but you can see how that's going to be a bit of a pain. It's got to detect in optimization that it has to do that. The other thing that it can do is it can basically say, I need to put a pipeline register here. I thought I could do it in the interconnect, so I didn't put it in the logic block. And I can't. I now analyze hold and it's not going to work. I have to change the routing. So what it can do is it could say, even though these are very close together, I'm going to actually say, go to there, take a routing driver, go vertically for no apparent reason, okay? Take another routing driver, go horizontally. Now, at this routing driver, turn on the pulse latch, and then go down here, and then go through another routing driver and go in here, okay? So it can intentionally detour the route. And by detouring the route, it adds enough delay that there won't be a hold time violation if it uses this register. And Cordis does have the ability to do this. It has some downsides. You're chewing up extra routing and extra power just to slow signals down. If you do that once in a while, it's not a big deal, right? It's probably a good solution. If you wound up with, this is a wide bus and you have this happening all over the place, then it could start causing routing congestion and a lot of negative consequences. Does that make sense? So in the figure that I showed you where it showed how much Altera predicted they would lose with hold time, they weren't asking the router to fix it. Okay, so with CAD optimization, they could do somewhat better than that because the router can try fixing some of them. Does that make sense? You do have a lot of things interacting now though. Like your router is basically, you have like retiming and register insertion and where you put them interacting with the router, so you can see how it turns into a very complicated CAD problem. Usually you have to make some decisions about how much you will iterate between your algorithms, and you try to minimize it for compile time reasons.
In ICCAD for larger design, you often have this where the tool tries to fix the hold violation, creates a setup violation, tries to fix that, creates more hold violation, and this keeps looping around.
Yeah, so in ASIC tools, they also have to do this. ASIC tools, you're right, so ASIC tools also have to do this. It's extra challenging, I would say, in an FPGA because a general technique in an ASIC tool is go insert buffers, right? You can do things like just insert a bunch of inverters, which could cause you problems if there's no spare room for putting inverters in. So usually ASIC tools try to leave some spare room in case they have to do that. In an FPGA, you can't just insert inverters. What you have to do is use the existing wiring. So in a sense, you can say, well, the wiring's already there, so maybe it's free, but it's also limited. If you run out of it, you're kind of in trouble. Does that make sense? So yeah, similar idea, but you have to use somewhat different techniques. Yeah?
Just to make sure I understand this correctly. So let's say if you are not using
Yeah.
regular levels, then you also need to ensure that your like basically you cannot go through, right? So your core can actually you cannot run before the clock actions.
Yeah, I probably didn't draw this that well, so I didn't draw this on paper in advance. I'm going to show you clock skew scheduling, which is another technique Xilinx uses, and I'll try drawing this again. But the basic constraint, let's see, maybe I should draw this. I'll draw it again when I do Xilinx, when I get to Xilinx's technique. Does that sound good? And hopefully then I'll draw it better, and your question will be answered. Otherwise, let me know. Does it make sense? Okay, let me turn on the projector again. Okay. Okay, so what was the overall outcome? So they increased area by 5% for the pulse latches, but then some more for the clocking and control, which they didn't talk about. There's a small routing slowdown from putting the pulse latch in, like even when they don't want to use it, but it's not stated in the paper how big that is, but it is small. Those are the kind of negatives. On the plus side, they have many more registers. So there are a lot more routing wires than there are registers in logic blocks. So it's a very register-rich architecture. And these registers can be reached without the logic block insertion delay. So this lets you retime logic more flexibly. You have more places you can put registers because they're all over the place, and it lets you pipeline very deeply because you have so many registers. In the paper, they say that if they take their benchmark suite, they get 45% speed up over Stratix 5, which was their 28 nanometer architecture, which doesn't have registered routing. And if they redesign to essentially pipeline more deeply, then they can get 92%. There's a lot of things mixed together here. Okay, so there's 2 levels of process improvement from 28 nanometers to 14 nanometers. They changed the routing architecture to try to optimize it further, exploit 14 nanometer. So you can't really separate out, exactly how much of this is from the registered routing. My very approximate guess would be that they might have gotten 30% from this when they do deep pipelining. But that is a guess. So I think it's significant. That is a pretty big win. Okay, so Altera feels they've got a pretty big win here. They built new CAD tools. So basically, the CAD tools integrated a lot of extra retiming. So they already had retiming, but after this, the Quartus will, for Stratix 10 and beyond, retime the design multiple times. Basically, before placement, after routing, basically trying to get the registers into the right spot and to decide which ones go in logic blocks and which ones go in routing. So they kind of retime it repeatedly, trying to converge on the best answer. And other tools that require designer, that's automatic. The designer input tools they have advisors basically that tell the end user, you could pipeline more here. You have a loop. You could try to restructure the loop so you could pipeline deeper. Basically trying to encourage people to pipeline more, giving them hints about how to do it. CAD tools can't automatically pipeline because it does change the latency at least of your design, which might not be okay with you. But they can tell you, hey, if you did this pipelining, it would help you. Okay, so since Stratix 10, Intel released another architecture, Agilex, and it backs off a bit. So in Stratix 10, they found the hold time was essentially worse than they expected. They couldn't turn on the pulse latches on 2 wires in series because they couldn't make the pulse narrow enough, basically. They would get that register run through or a hold time violation. That's not catastrophic. They just tell the CAD tool not to do it, but it means they can't use all the registers. The other thing is that in 10 nanometers, the wire resistance is higher than it was in 14, which pushed them in Agilex to change their routing architecture and have more short wires. As you have more short wires, it means if you have every routing driver can be a pulse latch, it means you're going to build even more pulse latches. But you already couldn't turn on 2 pulse latches in series, and when the wires get shorter, that's going to go from 2 in series to maybe 3 or 4. Like it'll be more wires. Like you have to turn a pulse latch on, you might have to go through 3 or 4 wires before you can turn another one on. So that made them think maybe it's not worth it to have like a register in every single wire because we can't use them all. And also, the pulse latch trick is making our hold time worse, which is why we can't use them all. So they switched to conventional registers, right, like master-slave registers in the routing, but they are more expensive. So to mitigate that cost, they basically only have 1/3 of the wires have registers in them. So it's still a lot. That is still a lot more than you have in the logic blocks, but they basically did change their architecture quite a bit. Yeah.
Like if you are porting designs from Stratix 10 to Agilex, and you are losing like 2/3 of the registers you would have, how
Yeah.
does it affect like designs where you have to have like
I think you're okay. The reason is because they have shorter wires, you don't really lose 2/3 because effectively you got more wires than you used to have, which means if they didn't change anything, you'd have even more registers than you used to have. Now, so let's say you've got 50% more wires because they're shorter. But then they only make 1/3 of them can be registers. So yeah, you've still lost some. Does that make sense? On the other hand, you actually couldn't use them all before. So you can only really use like half of them. Kind of best case, right? You're trying to use them all, but then it turns out the CAD tool says for sure you use one, you can't use the next one. So if you combine those two things, it probably means that in practice, you really have about as many registers as you had or fairly close. So I think it's just they couldn't quite get to the level of pipeline depth that they had hoped for before, and maybe nobody could practically do that anyway, so this still probably enables the same max pipe depth. Yeah?
I'm wondering during straight time design, like somebody would have thought, hey, let's do half the registers but make them regular registers of the clock first thing, because this is something unique that usually don't mess with the clock, and this is messing with the clock.
I mean, FPGA vendors, it actually has become a sport. You're going to see what Xilinx does too. They're all messing with the clock now. So, so that barrier's been broken. Yeah, I thought the post latch was extremely clever. I really liked it. And I wasn't there when they did it actually, but that was like, we did it in Stratix 5. And I thought it was very clever to put it in the routing. But yeah, ultimately, I guess the whole time wasn't good enough, so they went with the sort of a bit more conventional solution in the next generation. Yeah.
Did Ultra like explore HLS flows that automatically like add a ton of registers to like utilize the routing registers?
I don't think that was part of this architecture, although it basically would show up in their design suite. If HLS tools are making things more regular, more register rich, and then that'll show up in the design suite. Does that make sense? Like the architecture doesn't require that, but it will benefit from it. So, okay, so Xilinx, Versal has something that is their answer to register routing, but it's not the same. Okay, so Xilinx, Versal is their latest architecture, and they explicitly chose not to put registers in the routing. And I know like the lead architect of Xilinx is Trevor Bauer, and he said they've actually looked at it and they've come to a different conclusion. So they actually don't like registers in the routing. They don't think it's the best idea. What they did instead is, they've always had registers on their outputs, right? Like on the LED outputs, they have registers. And they can use those independently of the LUTs. What they decided to do, but they also did see the same trend that Altera is seeing, that designs are getting more and more register rich, and it does take multiple clock cycles to go across the chip. So they thought it could be beneficial still to have more registers. But instead of putting them in the routing, what they did is they put them on the inputs of the block. So they already had them on the outputs, and obviously you can use those, you can come in from the routing, and if you don't, you can get at those registers if they're not used by the LUTs, so you could already do that, but they decided we'll put more registers in on the inputs too. And there are more inputs to a block than outputs, so this is somewhat more, more than doubling their registers they had. Then the other thing they did, well actually look, so this doesn't look incredibly useful, because you can chop off a little bit of delay here, but if you were coming from a long interconnect path, and you were going to be timing critical, because you weren't going to make it to this register in time, registering you here only cuts out a LUT delay. Okay, so cuts a little bit off your critical path, but doesn't cut that much off. So it doesn't seem like that was super exciting. So what Xilinx did to make this more powerful is they add programmable delay chains on the clocks to the outputs and programmable delay chains on the clocks to the inputs. Okay, so if you're saying don't mess with the clocks, like just everybody in the FPGA world now loves messing with the clocks. Okay, so why did they do this? This is a picture from the Versal paper that kind of walks through this with an example. Okay, so they've got a flip-flop. It's got a long interconnect delay, so a whole bunch of wires, 1.5 nanoseconds. Then it's got some local routing and LUT delay that's small, 300 picoseconds, and then flip-flop. And then that flip-flop also feeds something else. So it's got a 1 nanosecond interconnect delay, goes through logic block, local routing, and LUT, and hits another flip-flop. Okay, so 2 timing paths, right? I've got a timing path to the input of this flop, timing path from its output to the next one. And if we timing analyze this, we have to see what's the longest path delay between flops. It's 1.8 nanoseconds, so our clock period is 1.8 nanoseconds. So everybody with me so far? If you're lost so far, you're going to be really lost later. Okay, so they've now got these input flip-flops. So first optimization they can do is they can say, instead of registering at the output of the logic block, the CAD tool can choose to move the register to the input, right? We'll use our new input register. And basically that moves 300 picoseconds is taken off of this path and added to that path. Okay, so we take the minimum of the two paths, and this path is the maximum, sorry. This path's longer, right? 300 plus 1 plus 300, so that's 1.6 nanoseconds. Okay, so it got a little bit faster, right? We were able to fine tune, sort of balance between this input and output path a bit better by using the input registers. But then what they can do is they say, well, okay, they can't do this automatically, but the designer could, just like in Stratix 10, be told you should pipeline more deeply, and they could use now the input and the output registers on both logic blocks. And if they do that, the longest delay is between flip-flops is now this interconnect delay. It's 1.5 nanoseconds. Okay, so it's a bit faster than the 1.8 they started at. But in Stratix 10, they can chop up this interconnect delay. They can put registers right in the middle of that. Xilinx can't. Okay, they could say, well, you should route into a logic block, but let's not consider that. What that delay chain is used for is they basically, by delaying the clock, they can programmably delay the clock to this flip-flop on the input of this logic block. And what that does is this one I'm going to draw. I'm going to try to draw it carefully. It basically is a form of time borrowing again. It's called clock skew scheduling. The timing constraint for setup here is that I can't have a delay. Like basically, this data must arrive by the next clock edge. Okay, so if the data takes 1.5 nanoseconds and my flip-flop has like a negligible setup time, let's say its micro TSU is 0, then I need 1.5 nanoseconds between clock edges. But if I actually turn on that delay chain and I delay this clock by, what did they delay it by? 500 picoseconds. Okay, so I put a 500 picosecond delay on this clock. It actually means that I have I need to get the data there. It's going to take 1.5 nanoseconds for the data to get there. But this clock edge is going to launch its data, and then I'm going to wait 1.5 nanoseconds. This clock edge is not going to arrive until 500 picoseconds later. Okay, so that means if the clock period is 1 nanosecond, I'm actually okay, because the next clock edge will be 1.5 nanoseconds later than this clock edge. I'll draw that out. So that actually means they can clock it faster, right? That means they haven't actually moved this flip-flop in space. They've essentially moved it in time. They've basically said, I'll delay your clock. By delaying your clock, if I delay your clock by 500 picoseconds, it is okay for this delay data to be 500 picoseconds late too, okay? Because it's just about your data getting there before the next clock edge. So if my next clock edge is 1 nanosecond later, but I also delay the clock to this register by 500 picoseconds, the total is 1.5. That matches my interconnect delay. That works. So they didn't physically move it. They essentially moved it in time. Now when you look at this is 1,000 picoseconds. This is 500 plus 300. That's 800. This is 1 nanosecond. This is 300. They could clock it at 1 nanosecond. Does that make sense? Yeah. Yes. So clock skew does not always hurt you, okay? And clock skew scheduling is a CAD technique where you intentionally start moving your clock edges around to basically make your timing constraints easier. They can do things like that to fix hold time too. Yeah. So they're not doing that in this case, but actually they can actually skew the registers to try to fix hold violations as well. Hold violations in so in FPGAs, usually hold violations are not a big problem because the programmable routing takes a while, and hold is always about data getting there too early. You generally only get hold violations in two cases. One is you're transferring data between phase-related clocks, and that means you might have a clock here, and you might have another clock that's only 100 picosecond away, and all sorts of crazy stuff can happen when you're doing that. So you could get a hold violation there, or you start messing with the clocks, right? So generally fixing the hold violations would be, we've made some hold violations by messing with the clocks. We could maybe do some more messing with the clocks to try to fix them. Does that make sense? I think I'm gonna draw this one out. So are people getting this, or you want me to draw out like what exactly is happening here? It also illustrates a pretty important principle of how do you actually analyze timing in a circuit. Yeah.
Just so that, I know you'll draw it out, but just to make sure that I'm clear on this. By offsetting the input to the logic block by 500 nanoseconds.
500 picoseconds, yeah.
500 picoseconds.
Yeah.
You've essentially given the interconnect delay, which is 1.5 nanoseconds, so 500 picosecond
Bonus.
bonus.
Yeah.
And then I guess you're saying because you're giving it a bonus, you're amortizing this to 1 nanosecond.
Yeah. So, yeah. Okay, so I'm going to draw it out, okay? So,
Like just for this one flip flop, the clock is going to appear later,
yeah.
but then the next flip flop will have less time.
Yeah, it is a zero-sum game. By delaying the clock to this flip-flop, essentially, from a timing perspective, it sort of appears like it's here. Okay, that's how they visualize it. I'll draw out the actual timing diagram. That made this transfer easier. I essentially borrowed time. I delayed my clock. It makes the next transfer harder, right? Because if I take this flip-flop here, now I've delayed this clock by 500 picoseconds. So I launch my data 500 picoseconds late. If my clock period is 1 nanosecond, I don't really have 1 nanosecond anymore. I used the first 500 picoseconds already by being late. But I actually here am okay. There was only 300 picoseconds. So if this was actually a pretty long delay, like if this flip-flop wasn't here, for example, then I couldn't do it. Because delaying the clock on this would make this transfer easier, but I'd fail the next one.
I guess you're able to do it only when the time you're borrowing is more than the delay you need.
Yes. Well, so whatever time you borrow from making the timing constraint on your input easier, you make the timing constraint on your output that much harder. So it's useful when you have an imbalance in basically the amount of delay on your inputs versus the amount of delay on your outputs. Does that make sense?
Because like the next stage is 300 picoseconds, but you're fine with that because that's pretty fast.
Yeah, so my clock's delayed 500 picoseconds. So I launch at 500. I have 300 picoseconds of data delay. That's 800 picoseconds. I still arrive here before the next clock edge, which was at 1 nanosecond. At here, I launch at 0 nanoseconds. I take 1.5 nanoseconds to get here. And then I compare that to, I have a 500 picosecond clock delay plus 1 clock period, right? Because I'm always checking in the next clock cycle. That's 1.5. I just barely made it. But if I didn't have that 500 picoseconds, I didn't make it. I was 500 picoseconds too late. Does that make sense? Okay. Why don't we take a break for 10 minutes? I'm going to try drawing this on the board. That actually allows me to iterate on it and see if I can draw something proper. So to go through the timing diagrams on this. We'll see how this goes. So Hale, are we live? Oh, I should mention too, I have, if you want your physical midterm back, see me after class, okay? Because I have the physical copies here. Yeah.
Do we know when like the assignment to like the assignment to like results come back?
Yeah, I basically didn't quite manage to get them in the slides. I have them. They'll be in next lecture. Okay? So, oh, you mean like the marks, or you mean like who got what?
Well, I guess who got what?
Like I have them, but like this class is insane. Like basically I have to go through with Sohail. It's like, wait a sec, but people are using all, to compare them is more complicated than I thought, because people are using all sorts of crazy optimizations, which is good. So that's all good. It's just basically like I got to go through with Sohail and figure out how to bring some kind of order to this, or how many Amazon gift cards I will. There could be several, because depending on which dimensions we cut it on, there appear to be several winners. So how about next class for sure, okay? Okay, so let me try to like show you this clock skew scheduling and timing constraints on an example. So this might be a little messy looking, sorry about that. Let's see, let's get rid of this. I don't know why I put that there. That doesn't need to be there. Okay, so this is the case we just did. We got a register A. It goes through a whole bunch of interconnect, takes 1.5 nanoseconds, gets to a logic block. In Versal, you can turn on registers on the input and on the output, and we're doing both those things. Okay, so we got this timing path of 1.5 nanosecond from register A to B, and then a very short one from B to C, right? 0.1 nanoseconds through the LUT. Let's say our desired clock frequency is 1 nanosecond. So the way I analyze that is, okay, you take the clock at register A, and I've just drawn out a 1 nanosecond clock, very simple. I need to get the data to register B in no more than 1 clock cycle, okay? So I basically draw what is the clock at register B, and I'm going to use clock skew scheduling. I've already decided this is 1.5 nanoseconds. There's no way I'm making timing without delaying this clock. So I've delayed this clock by 500 picoseconds. And that's what Vivado would do for you if you're using this optimization. So this is the clock at B. And notice that it's not aligned, right? This has been delayed 500 picoseconds. So if you look at that carefully, you'll see I've actually shifted it all by half a cycle. Does that make sense? Okay, so the actual setup constraint is I must get from clock A to the next edge of clock B. Make sense? That's actually what setup means. Setup means get me there in 1 clock period. So I go from this edge to the edge 1 clock period later. But it's the edge at B, okay? So that actually is not 1 nanoseconds later. That's actually 1.5, because clock B has been shifted by 500 picoseconds. Does this make sense to everybody? I have to check, is my whole data path delay, my longest data path delay between register A and register B, less than that, okay? It's 1.5 nanoseconds, so I just barely made it. It's equal, maybe that's a little marginal, but we're gonna say equal is good enough. Does that make sense? People also ask me, like, what am I talking about with these micro TSUs and so on? So this, if you look at how Quartus does this, and it's probably typical in most tools, you'll actually see that there's like a micro TCQ at the start of this. So the first part of that 1.5 nanoseconds is this parameter that is basically the register delay. What's the delay to get out of the register? And at the very end here, you'll see there's a micro TSU. The micro TSU is like the register itself, just by itself. Does it need a little bit of time to capture the data? That will be added in I'm adding that into this 1.5 nanoseconds. So most of it is all the routing delay, but at the very start and the very end are these little register parameters. And I made timing, like I met my setup constraint by shifting the clock. So is everybody with me? That's why this is a useful thing? Yeah.
So I guess like a simple way of saying this is data needs 1.5 nanoseconds. I can do that either by having a 1.5 nanosecond clock,
Yeah.
or shrinking the clock and then making the distance between launching edge and capture at 1.5 nanoseconds.
Yeah, yeah. So it's actually, what is exactly. I have a it's actually always better, I think, to think in terms of edges. That's the exact way I think of timing. So you have a launch edge, which is here. Your capture edge is 1 clock cycle later, but at the destination register. If I shift the clock out, it actually makes my capture easier. Okay, that sounds maybe a little too good to be true, and it is. I mean, everything I said is true, but now what we have to also check is hold time, right? Because otherwise we could just say, let's just shift all the clocks by an infinite amount of time, and our circuit is infinitely fast. And like, I'm like the world's best 241 designer. It's unbelievable, right? So here's my clock B again. Your hold time is basically on the same cycle. You cannot get the data there by even the shortest path, right? It's the contamination constraint. Clock hits your design, starts moving all the way through all your registers. No register can basically affect a register in the same clock cycle, right? Because that just breaks synchronous design. If you want to affect it next clock cycle, not same clock cycle. So basically, I have shifted this clock by 500 picoseconds. So if I hadn't shifted this clock by 500 picoseconds, my hold is very easy, right? If I have good quality clocks. Basically, because if this clock B was aligned, it would be almost impossible for me to get data there that fast, right? But I've shifted it by 500 picoseconds, so now if my data can get there in less than 500 picoseconds by any path from A, I'm in trouble. But A actually has only one path here, so it's okay. Technically, you have to analyze this at all process corners. So I've been using like one delay. What Vivado or Quartus would do is it would also say, well, what if this chip is being run in like Northern Ontario, and it's the world's fastest chip, and the voltage is high, and so on. This 1.5 nanoseconds, probably drops to like maybe 1.1. That's actually still okay. Okay, does that make sense? But you have to check. So these are a little harder to meet because you have to check this when your delays are the smallest they'd ever be. Here's another case. Okay, so data D launches its data. I've got 1.2 nanoseconds of routing delay. Then I go through a LUT. That adds 0.1 nanoseconds. Then I go through a little bit of interconnect delay into a flip-flop in another logic block. That's another 0.1. Okay, so the path from D to F is a total of 1.4 nanoseconds, right? Everybody with me? I just add all those up. I'm just tracing routing, LUT, little more routing, adds up to 1.4. That's my data D to F delay. If D, okay, so let's say I use the same trick now. I basically say, well, that delay is bigger than my clock period, so I'm not going to meet setup time. So I'm going to shift my clock F. Okay, shift it by 500 picoseconds again, and now I should be fine for setup because I need to check from this clock edge at, well, let's say this is both A and D. Okay, so from this clock edge at D, I need to go to this clock edge at F, which is like 1.5 nanoseconds away, and that's more than 1.4, so I'm okay. Does it make sense? So it all looks good. But in this case, I've also put another path in. Okay, so there's a register F. Register F has like just some local interconnect inside the logic block, so 0.1 nanoseconds, goes through the same LUT, 0.1 nanoseconds, a little bit of interconnect, 0.1 nanoseconds, and reaches F. Okay, so from, okay, this is actually 0.3. I didn't add that up properly. Okay, so from data, the data path from E to F is only 0.3 nanoseconds long. Does that make sense? And let's say I also have put E on this clock. So now I got a problem, okay? Because my constraint, my hold constraint for E is I launch my data here. My contamination edge is there, right? That's the same clock edge. And this has been shifted by 500 picoseconds. That's actually more than the minimum data path delay. So I actually have a hold violation. I can get my data there in the same clock period, which is called contamination, right? I've broken my design. So I would not, the CAD tool won't allow this to happen. Like basically it would say I can't shift this clock by 1.5, I can't delay this by 1.5 nanoseconds because you get a hold time violation. Now what it might do now is say, well, what if I also shift this one? Okay, so it can, clock skew scheduling turns into, with a CAD tool does it, it's more complicated than me just putting one delay on things, because the CAD tool could go, I got a problem with this one, maybe I can shift its clock, and it actually goes off and tries to shift all sorts of clocks. Does that make sense? And if it could delay this, shift this one and off, it could be okay. It could also tell the CAD tool, I need you to just make this routing delay longer. Okay, so you were just using local interconnect, but for no apparent reason, you're now going to leave the logic block, route around it once, come back in. Okay, and if I did that, and this 0.1 nanosecond turned into, say I took the 1.1 and I made the routing delay to 0.4. Okay, now my total data path delay would be 0.5, 0.6 nanoseconds, and it'd actually be okay. Okay, so there are ways that it can fix it, but you can see how there's a whole lot of simultaneous constraints. Does that make sense? I guess the number one thing I want you to get out of this, because lots of students don't get it, is what is setup really? And setup is get there in one clock period. From the launching edge at your source to the capture at your destination, you have one clock period. Hold is from the launching edge at your source to the same edge at your desk. You cannot get data there. Like there's no path that gets you data there to that same edge. Does that make sense?
Get from launching edge from source clock to capture edge on source, the same clock. That's the same.
Yeah.
And then hold is you cannot get data from the launching edge of one clock to the launching edge of the other.
To the same launching edge, basically.
To the same launching edge of the
Yeah.
other. You can't have it change.
Yeah. So it's kind of useful to think of sort of like the base clock these are derived from, so that you can sort of label the edges. This is like edge 0 and so on. When you write, you don't normally do this, but you actually can write more advanced timing constraints in SDCs. So in your assignment 1 and 2, I wrote a simple SDC for you. You can actually tell the timing analyzer, I'm actually not aiming for this edge, I'm aiming for this edge, right? And that's called a multi-cycle. So you could actually say multi-cycle equals 2, and you're actually telling it, I'm aiming for this edge. Now, if you do that, you actually have to really know what you're doing, okay? Because you can't just say, it turns out that if I say that, the tool says my timing is good. You have to have a reason that you said that. Like, such as, I actually know that I only enable this block every second cycle, okay? That's actually a valid reason to do that. But you need a valid reason to do it. You can't just say, I think I'm gonna aim for the millionth edge, and let's see what happens. Like, Is actually, so most designers never write those kind of constraints because they're quite error prone. Like first, usually you can't, you didn't design your circuit that way. And then secondly, when you do write them, you have to be super careful because if you write them wrong, the timing analyzer says your design works and it doesn't really work. So this is what it does by default, which is what most people want, right? Get me there in the next clock cycle, don't get me there in the same clock cycle. Does that make sense? Hopefully I didn't confuse you with the multi-cycle. The multi-cycle is if you know additional behavior about your circuit, you can start saying, I know secret stuff that you can't figure out, but you really need to know that secret stuff. So. Okay, so let's see. Okay, so hopefully you can tell me in the evaluations or afterwards whether that digression was worthwhile or not. So tell me after class, all right? Okay, what do you think the pluses and minuses of this are versus Stratix 10? Yeah.
I guess the big minus is you can't really pipeline increase
Yeah, yeah, so it fundamentally can't pipeline as deeply, you're right. You get like kind of 2 pipe stages per logic block, which is not bad, but it's not as much as getting it all over the interconnect. Any pluses for this? Yeah.
Doesn't slow down like every wire.
Yeah.
Even though they said it was a small slowdown, it's trying.
Yeah, yeah, to keep their wiring simpler, faster, smaller. Yeah.
But it does slow down our local interconnect across.
It slows it down some. You're right. You put these extra registers in there. So, but I guess because you're only going to go through the local interconnect kind of on the start and end, it's probably not as big a deal. But you're right.
A mux and a drop on every input of every not even like logic block. That's a large area.
Let's see. I guess they do it actually on the logic blocks, right? So it's like every input of the logic block, they put a 2-to-1 mux or some equivalent structure that allows you. Is a 2-to-1 mux either go through the register or not. So that 2-to-1 mux does add a little bit of signal delay. They do it on the inputs of the logic block. So yeah, I think it's on the inputs of the logic block, which is fairly close to the LUT inputs, but I guess not exactly there. It's before the local interconnect. Yeah.
There's no limit to how much you can pipeline the interconnect delay with this, because like you can't go like if the COV delay is high enough, then you can't too much time.
Yeah, yeah. It basically, fundamentally, they can sort of split this thing, split an interconnect delay with a register, but they can't put like 12 in. Now they do have if they have some unused registers in their logic blocks, they still can do the thing of route into the logic block, but they get the insertion delay. So, yeah. Okay, so good ideas. So what did I write down? Okay, so it's less area, less timing overhead because it slows down block inputs, which is less frequent than every routing wire. Oh, this is one that I didn't talk about. So the registers that Stratix 10 puts into the interconnect are simple registers. They don't have clear signals, which means that sometimes if you put clock enables on your registers, for example, they can't be moved into the interconnect because it's too complicated. Like they don't know how to get like a clock enable and a data signal to the register. So only simple registers can be moved into the interconnect. Quartus has algorithms to try to like kind of pull, if you have a clock enable, to try to pull the clock enable out of that register and put it in the logic before it. So it tries to mitigate this, but they have full featured flip-flops here. So they're less numerous, but they can kind of do everything. Yeah.
I remember from the Agilex paper, I think that was reading, they mentioned that in order to deal with the clears, they put synchronous clears, asynchronous clears, so the same thing.
I think they basically in modern FPGA design, they recommend that you don't use asynchronous clears. Synchronous clears are easier to deal with. So,
I guess, could that hit like that idea of putting clears up and unifying clears without
I mean, the problem with the simple registers, like you can do it with a pulse latch, but basically you still need some logic in front of it. The way you do a clear or a clock enable is like a mux for a clock enable, and for a clear it's like an AND gate, and they need an extra signal. So your problem in the interconnect is you've got this data flying by, and you just got like one signal. You want to register that one signal, but if it also needed a clear or a clock enable, you don't really know how to do that. Like the clear and the clock enable are effectively logic. So if you started putting those in your interconnect registers, you'd start making sort of a logic block in your interconnect, and eventually you could draw a box around it and say it's a logic block. Do you know what I mean? So I think it's pretty hard to think of how would I put clock enable in an interconnect register because of the fact it's just another signal that I need to bring together now.
And then, like, I guess it'd be the same idea for clear.
Yeah, it is a similar idea for clear. Now Quartus does things where they basically, if it can guarantee, it's got a bunch of fairly clever algorithms. So things like, I clear this register, and then there's a sequence of registers after it, and therefore I can guarantee that all those registers will be cleared within, after you clock it 5 more times, and maybe that's good enough. Do you know what I mean? So if you can prove that that actually is equivalent, and there are algorithms in Quartus to try to prove that, then you can actually move logic with clears in. And that's why they actually like things like synchronous clear. It tends to be easier to prove that. Yeah.
Most designers just tend to write if reset at the start of every block. So how does it get around that?
It gets around it with those proofs. Like it basically, if it can prove I cleared the first register in a chain of pipeline registers, and I clear that, and all the other ones are like time-shifted copies, that it's always going to be okay by the time I care about it. Do you know what I mean?
In my simulation, when I still see like axis bubbling through, that's going to be very.
I don't know. We've got a couple of people from Altera here, so I think I'm going to defer that one for them, right? Like so. It was. I know it was. There were a lot of things I had to think about to do it. So I don't know if anyone from Altera wants to handle that one. So it's a good question. How well can you hide it? Yeah, it allows deeper. This allows deeper pipeline, but as you said, pipelining. But as you said, it doesn't allow as deep as Stratix 10. And yeah, this clock skewing circuitry makes their flip-flops better at kind of splitting up long interconnect delays. Okay, so let's go on to clocking architecture. So we've talked a bunch about routing architecture, but we also need to get clocks. So should we build special resources for clocks in FPGAs, or can we just use the regular routing? I mean, we can use the regular routing to do anything we want. So maybe we're done, right? We can be done this section super fast. Just use the regular routing. So what do you think? Do you like the idea of using the regular routing?
I mean, like coming from like a basic flow, like the clock is a high switchability net, and if you want to route it, you want to make sure that it's kind of isolated and it's shielded from other nets, because you don't want other nets that are switching to affect it. It's a high criticality, high switching net as well.
Yeah, that's a great answer. So it is possible to route on regular routing, but there's a lot of downsides. And one of them is exactly what you just said, what's called crosstalk. Okay, so wires are capacitively coupled to other wires. Their delay is affected by the switching of wires near them if you don't shield them. Shielding basically means you put like something that's ground or VCC in between the wires, and then there's very little capacitance to the switching wires then. On data paths, you don't really worry about this because all the simultaneous switching does is change your delay. So your delay model has to kind of estimate how much switching there is and take that into consideration in the delay. But on a clock, it's extra bad because if your clock basically if the edge is getting sped up sometimes and slowed down sometimes, your timing analyzer has to account for all of that. So it basically has to take the whole range of delays your clock could ever have and essentially assume the fastest ever when it hurts you and the slowest ever when it hurts you. And hopefully from that analysis I just showed you, like one of those on setup, for example, your clock, the slowest clock might be the thing that hurts you the most, and then the timing analyzer will use that. And on hold, the fastest clock might be the thing that hurts you the most. So on the capture edge, this is the case. The fastest clock hurts you the most on the capture edge for setup, and on hold, the slowest clock hurts you the most for the capture edge for hold. So the timing analyzer has to take all possibilities into account. So if you've got a lot of crosstalk that is basically moving your edges around, it all comes out of your timing in both directions, which is nasty. Yeah?
There's going to be a lot of skews. You can't guarantee that the clock is balanced all parts.
Yeah, so you also tend to get a lot of skew. So skews different delays to different points in the circuit, and we just talked about like basically clock skew scheduling where you skew things on purpose. But basically if you skew things at random, it usually doesn't work out very well, right? Usually you wind up some hold violations, some extra setup violations. And the regular routing is optimized for getting data from A to B in low delay. It's not optimized for building a tree that basically minimizes the amount of skew.
I guess it will also reduce your routing flexibility. Clock is guess they could have wires with it, and some of those wires might be quite useful, but the time critical, specific blocks.
Yeah, it'll also compete for regular routing, which probably would be okay if you just built more regular routing, but you have all these other issues. Do you know what I mean? Okay, so you can build clocks from regular routing, and actually most FPGA CAD tools will do this. So if you basically tell them to do it, they'll do it. If you run out of special clock resources, they'll build it out of regular routing. But you got a bunch of things. First, you need a low skew routing algorithm, which can be written. Okay, so what I mean by a low skew routing algorithm, yeah, maybe I'll draw this quickly. So the regular routing algorithms in FPGAs are trying to minimize the amount of wiring, get rid of congestion, and minimize delay, especially on the critical path. So if I have a signal like this, so some net coming out of here, and it wants to go, maybe here and here, it would do something like maybe take a routing wire like that, then a routing wire like that, then a routing wire like that. Okay? And that looks pretty direct, so it's pretty fast, it's pretty good at minimizing wiring. But it has a pretty different delay to there than there. For a clock, this is not great. So if I said this was a clock, and these are both registers, I basically got a lot of skew, right? Maybe this was like 1 nanosecond, and maybe this was 3 nanoseconds. And now when I do all that analysis of my capture edges and so on, they're pretty different, and that generally doesn't work out very well when it was just random, right? Like I showed you how you can do it on purpose to help you. So if you did this on standard routing, what you'd actually want the router to do, and you can make an algorithm to do this, is basically try to route equal delay paths for all of this. So you'd actually want it to do something like this. Route out here, maybe take a couple wires, get out here, then go down here into this one, and go backwards over here into this one, okay? Because that is actually more wiring, and it's less direct, but the idea is that it might take 3 nanoseconds to both, and that minimizes your skew. Okay, so if that was our only problem, we could write that algorithm. But even if we wrote that algorithm, it won't make a really low skew topology because the routing patterns aren't really optimized for it, right? They're optimized to try to minimize congestion, allow you to build fast routes. They're not really optimized to say, make this exactly balanced. So I probably wouldn't get 3 nanoseconds and 3 nanoseconds. I might get 3 nanoseconds and 3.3. So it's a lot better, but I probably wouldn't be able to line it up perfectly. We're going to get crosstalk, okay? So I've mentioned this quickly, but basically I've got a wire. So if I think of like physically, what does a wire look like? So it's basically a box in space, and there's a wire beside it. So these are both programmable routing wires. These basically form a capacitor. So if I basically have this wire is going from low to high, because this routing driver is trying to drive it high, and this one is going from high to low at exactly the same time. If you work through all the equations of this, they capacitively couple. This is going to slow this one down, okay? If I do it the other way, if I say, well, what if this one is going low at the exact same time this one's going low, they actually help each other, right? So it'll actually make this one faster. And on a clock, that's undesirable because it means I've got this clock edge that I don't know exactly where it is. Some cycles it's there, another cycle it's moved out a bit, another cycle it's moved back a bit. That's called jitter. And I have to basically take that into account in my timing constraints. Essentially, you have to add that jitter you have to take it out of your analysis for both setup and for hold. Like it hurts you on both sides. So you don't like it. You really want to minimize jitter. The other thing is when you analyze a clock, you can't analyze just what is it on like the average chip. You actually have to say, what's the worst case that I could get in terms of skew? Like, what is the fastest these wires could be, and what is the slowest these could be? And then vice versa. What's the fastest these could be, what's the slowest these could be? I have to take all those into consideration. And the regular routing is not optimized for variation. The basic way you optimize something for variation is you make the transistors bigger, and you try to make the layouts very similar. And we don't do that in the regular routing. We actually try to make them as small as we possibly can to hit our speed target. And that, again, that leads to something called clock uncertainty, which is essentially very much like jitter. Like, I don't exactly know where my clock edge is on these various registers. I got to actually guard band by that much in my timing analysis. Okay, so I guess I mentioned all these things, right? Skew will tend to hurt you, and jitter and uncertainty will for sure hurt you. Yeah.
Also, the fact that clocks are high fan-out nets, and it feels like the FPGA routing is more for like A to B rather than high fan-out.
It's pretty good for high fan-out. You can take a signal with 10,000 fan-outs and stuff, and you can route it fine. I mean, you may be right, like that the clock networks definitely are optimized for high fan-outs, so they may be even more optimized, but really high fan-out nets will route pretty well on the regular routing. Yeah?
You said to optimize for variation, you make the transistors bigger and can you see?
You try to make the transistors bigger, and you try to make the layout regular. The regular probably is less important than essentially making things bigger. Clearly, there's a downside to making things bigger, right? So there's a cost, so you'd rather not make everything bigger. But clocks are a spot where you really don't want much variation. Okay, so hopefully that convinced you we need special programmable networks for clocks, so we got to build them. So clocks are built with low skew structures. So kind of the classic structure for building a clock is called an H-tree. So I've got a buffer here. See if I can actually draw on this again, see if the computer's happier with me. Okay, so this is like my minimally programmable clock network. So I've got a routing mux that lets me choose what's going to drive this clock network. And then it basically, I drive a piece of metal here. It's going to be generally high in the metal stack, relatively wide, relatively big transistors to minimize variation. And then I hit this point and I go through a buffer and I drive 2 more pieces of metal and so on. And I make a whole bunch of H's. So that's why it's called an H-tree. And what it does is if I have a register that is quite close to me, say here, I follow a path that's pretty long. And if I have a register that's pretty far from me, say up here, I follow a path that's essentially the same length. Okay? So it doesn't give me the minimum delay that I could get to a spot. It gives me like essentially the same delay to everywhere, or as close as I can build. And that's what I want. It's like, give me a low skew network. Okay, so we could build an H-tree like this for every single clock. And the good things are H-trees are low skew because of their topology. We can build this high in the metal stack. You shield it. Okay, so I can basically, it costs me more metal area, but basically shielding means I have a clock wire here, right? So it's my box in space. Most of your capacitance nowadays is to metal wires that are beside you on the same metal layer. So I basically take the 2 wires next to it and I ground it. Okay, so that's a ground, and I make this a ground. Okay, and then I could use the next wire again. So the next wire would be this would be a clock, but this one's a ground as well. So shielding basically means I need to use twice as much metal. I have 1 wire, 1 shield, and I can repeat that. But once I do that, I have very little crosstalk. So that means my signal delay is not going to be changing cycle by cycle, and I won't get that jitter. And I guess I already mentioned this. Use wider metal, bigger buffers, and that'll reduce my process variation. Basically because you just get statistical averaging, right? You make really small transistors, there's more variation in the dopant, because one less dopant atom matters more. Same thing for narrow metal, right? You get a certain amount of under etch or over etch, it's a larger percentage difference in your metal. So make things bigger, they're less susceptible. Okay, so we could do this. Any downsides to this? What do you think?
I guess this is more of a, like, I guess if you have many clocks, that's many branches,
Yeah.
approaching a lot of wires.
So you think it's expensive? Yeah, and that's right. So it is expensive. Okay, so let's see. So we can, it's exactly what you just said. So we can have a lot of clocks in an FPGA design. A lot of them tend to be near IOs, right? So PCIe, DDR, SONET is an optical standard, et cetera. So for example, like one of the IP cores that I worked on, DDR3 needed, depending on the settings, 5 to 7 clocks just for one DDR interface. You could have 6 of them in a design. You usually have a few big ones. So you have where most of your processing is happening, those system clocks, they're usually pretty big, you know, tens, hundreds of thousands, maybe even millions of registers on them. But then you'll actually wind up with a bunch that are much smaller around the IOs. And you sometimes have one system clock, but you often have multiple system clocks. So if you basically got data coming in from different interfaces at different rates, you may still be doing a lot of processing on it. So you can have several different system clocks. So we could pre-build 100 H trees to basically handle our 100 clocks, but it gets expensive. So for H trees, the biggest cost is near the root. Okay, so you see like there's one wire here, one wire at the root. It's near the leaves where things start getting expensive. We have 2 wires at the next level, 4 wires at the next level, right? It's a binary tree, you see, maybe it's 8 and then 16, it'll probably stop there. But where most of the wires are is near the leaves. And the leaves are basically gonna be in individual routing channels. So if we build 100 routing trees, we have about 100 wires per channel. And that's approaching the kind of channel width that we have for the regular routing, right? So for a commercial FPGA with a reasonable sized logic block, usually your channel width is like 200 to 400. So 100's a lot, especially because we want to make these wires extra thick and shield them and so on. So they're going to probably cost us around as much metal as we're already using for all our regular routing. So it's expensive. So you could build this, but it doesn't seem super optimized. Okay, so what could we do? So how can we do better than this? Yeah.
Even regular ICs, you only build HPs up to a level and then you just do normal routing, goes to that.
Okay. So you're saying go H tree part way down, but then switch to something else that might be a little more wire efficient. So that's a good idea. Anything else we could do? Yeah.
Like spatially partition the chip.
Okay.
This section can like this can only use like 5 clocks. This section can only use 5 clocks.
Yeah, that makes sense. So basically we can have 100 clocks, but we can't have 100 clocks to go everywhere. Like it doesn't really make sense, right? Every register has 1 clock, so while we can't have 100, there's no possible way we can have 100 to go everywhere. It doesn't make any sense. So you're saying spatially partition it, build some smaller clocks. Make sense? Yeah.
I guess so you can have different issues, different sizes, and kind of stack them on each other. You're trying to path the clock to the entire wire on the side, middle one.
So you're trying to put the wires on top of each other? Is that what you're saying?
Like half, I guess, in a way, still proficient because you don't really need all the clock going everywhere.
Okay. So you're saying kind of spatially partition them again? Is that right? Okay. So do you have an idea, Robert?
Like maybe have a super high frequency clock, but only one.
Oh, okay. So build some better clocks and some cheaper ones. That's a good idea too. Okay, so a bunch of those things get done. So the first one is kind of spatial partitioning. So you can build some big and some small networks because you can't have 100 system clocks that go everywhere. So a technique that's often used is for example, many Altera chips will build 16 global clocks. So it's basically 16 clocks that go everywhere, so full H trees. And then effectively, if you just separate the next quarter of the H trees, like you basically don't build the top level. Instead, you build like a mux to access this level, this quadrant. Essentially for the same area or a little bit less area than a full H tree, you'll get 4 smaller H trees, like that each cover like 1/4 of the chip. So if I did that, I'd get 16 full H trees and 64 smaller H trees that each cover a quadrant. And then I could continue this, right? I could make some smaller still, and then the CAD tool has to pick what kind of clock should I use to span the part of the design that this clock needs. So that is used. Another thing you can do is most of the metal is kind of down at the bottom of the clock tree, at the leaves. So it's essentially the idea you had of like, well, let's switch to a different topology near the bottom because it won't add that much skew, but also add muxing. So, okay, so what I could do is I could build, for example, 16 full H trees, and I'm going to build 16 quadrant clocks in each quadrant. So same thing I just talked about. So let's stick with that. That means I've got 32 clocks accessible to any flip-flop. right? You can reach 16 global clocks can reach you, and 16 of these smaller quadrant clocks can reach you. But what I can also do is I can say, well, let's take a region. And in a lot of Altera devices, this was 1/8 of a row. There's nothing magic about that, but you can take like a fraction of a row and basically say for that fraction of a row, let's say there's only a subset of those clocks available. So we basically build muxes. So that's what this is showing here. And those muxes choose from the 32 clocks that have made it this far. But we only pick, again, this is a bunch of Altera devices, 6 of them, okay? And those 6 of them now, that's like now we're down to 6 wires instead of 32, and those span 1/8 of a row. So we have lost some flexibility. If we put a flip-flop here that needs that needs a different clock, it's not going to work. So the CAD tool basically counts how many different clocks do I need in this relatively small region, like 1/8 of a row, and it basically forbids any placements that would use more than 6. And that's enough that you can guarantee after placement's completed that we can actually configure these muxes properly and get the clocks everywhere. And the 6 isn't random. So we, in Altera devices, again, we use this a lot. The 6 came from experiments. So in Stratix, it was 8 because we were worried. And the experiment said that we could do it with 6, but we didn't trust it. And then in all future devices, we went to 6 because we trusted the tools more. Basically, if you went all the way to 4, we found that the placement engine now started to lose a little bit of quality because it was having to work harder to meet this constraint. But at 6, it didn't have a noticeable impact. Like it could legalize things without really affecting wire length or timing. So you could push this even lower, but this is where, architecture is again empirical. We found pushing it lower saved a little bit of area, but started having negative effects on the placement and what else we could do. So this structure is often used in FPGAs. So this is an H tree, and then this last part is called the spine and rib clock. So the spine is this vertical thing, and then it fans out to individual rows or ribs. It isn't quite as low skew as building an H tree at this point, right? Because if you come out of the middle of the spine and go along this, a little bit along here, your delay is a little bit less than if you came off the end of the spine and went all the way across. But that skew's not that big, so as long as you don't make the spine or the rib too big, you save metal with this topology and your skew's not too bad. Yeah?
Is it possible to do it like non-uniformly throughout the device? Like on the edges, you have more clock flexibility and the middle you have less?
Yeah, you can do that too. And there are some special I/O clocks that are often in various FPGAs as well. So you can wind up with like essentially things that are not H trees. The way Altera did this is we always used this structure for the lowest part of the clock. And we did use like these full H trees, quadrant H trees, but we also added in things that were called like I/O clocks. And they were essentially, sometimes you just had like a PCI Express signal came out and went straight into one of these spines. Does that make sense? Or you might do that for various I/Os might do that. So you had the ability to make a bunch of very small clocks. Does that make sense? And yeah, you do mix all of those things. Okay, so Stratix 10 changed this a bit. So instead of, what Stratix 10 did is it basically made the clocking a bit more flexible. So what I've shown you is basically most of the Stratix series. They use this structure. What Stratix 10 does, let's see if I can walk through this, is they still use this. Okay, Stratix 10 still uses this bottom part. Okay, so it uses the spine and rib and this muxing structure to say you've got these row clocks and so on. So you still use that. But instead of pre-building some H trees that cover the whole chip, some H trees that are smaller that cover a quadrant and so on, what it does is it basically has a new routing network that is just for building the top level of clock networks. There's only 32 wires in it. Okay, so its channel width is narrower, and it's only in certain channels. So it's basically, these are between relatively big regions of the chip called clock sectors. All of these wires are shielded, they're big, etc., so they're suitable for building clocks out of. And the topology of the switch network is good for building H trees. Okay, so it's kind of optimized for fan out. And basically, Quartus has a CAD algorithm that can essentially use these wires that are designed for top-level clocks to build. You can build like an entire H tree out of it, or 32 H trees out of it if you want. You can build smaller H trees, like quadrant H trees and so on, but you can build like sort of more irregular things, like basically pieces of H trees that fit together any way you want as long as you don't run out of these 32 wires. And then when you get far enough down in the H tree, it switches to that same structure I showed you before, the spine and rib with some muxing down to just 6 signals. Does that make sense? So you think of it as kind of like a network optimized for building the top levels of H trees, and then a routing algorithm that can build you any kind of H tree or thing like that you want. Yeah?
And could this be used for like set signals or stuff like that too?
You could, but yeah, you can. With synchronous resets, you don't really need to, because synchronous resets behave just kind of like any other signal. You don't need them to be low skew. You just need to get there in a single clock cycle.
But just since it's like also a side channel.
Yeah, you could use it to put it on there, and some designers do. So usually the skew of these networks is good, but their delay is actually only so-so. Like they're not optimized to be the lowest delay. Now, if you went everywhere on the chip, they might still be a pretty good delay path. If you don't go everywhere, usually putting it on a clock network is actually slower than just going through the regular routing. Okay, so what is Xilinx doing? So one of the things Xilinx did in UltraScale, so the chip before Versal, but Versal inherits this, is more clock skew scheduling. So what they did, their clocking at a high level is similar to what I showed you for Altera. So they have these pre-built H trees, and at the bottom level, they have a spine and rib structure. Okay, so Altera's spine is vertical and their ribs are horizontal. Xilinx is, let's see, I guess that's still what it is showing here too. So it's a spine that's vertical and then the ribs are horizontal. So a similar thing, there's an H tree above this. I'm showing kind of the lowest level. So far, and they do this muxing of, pick how many from these spines, pick a subset of the clocks and send them out to the rows. Okay, so similar so far. Actually, no, sorry, I screwed this up. This is essentially the equivalent of a row clock in like the last stage of clocking in an Altera device. So it's rotated 90 degrees. Okay, and this is the equivalent of a rib. Okay, but they do it, their rib is horizontal, or their spine is horizontal, their rib is vertical. So just rotate the previous picture, and it's the last part of the clock network. So hopefully this looks, once you rotate it 90 degrees, it looks pretty familiar. But the interesting thing that they did is they basically put the ability to skew the clock. And they do that not in every single logic block. To keep it cheaper, they do it on what they call, I forget what they call them, but essentially these are what I called like the row clocks in Altera. They're like the last stage before you get into the CLBs. They might span 32 logic blocks. They also have AND gates, so they can gate the clock to save power. Let's see. Okay, so the thing that I'm most interested in is this, right? So this is a delay chain again. So they send the clock in here, and it goes through a bunch of buffers, and they can choose with this mux basically to take the original clock or to take a clock that's delayed by 60 picoseconds, 120, 180, 240. So they can choose to delay the clock if they want before they send it out to this last stage of the clocking. Okay. There aren't that many of these, so they basically add less than 1% of the die size to make these delay chains. Because they're kind of partway through the clock tree, there aren't that many of them. And now they can skew the clock to groups of registers. They can't skew it to one register at a time, but they can basically skew it to something like 30 logic blocks. They can skew the clock to it. But the thing is, they also don't just select one clock to send out. Xilinx selects 16. So they could send two versions of the clock. They could send an undelayed and a delayed, and these logic blocks can pick what they want. Okay, so they have a reasonable amount of flexibility. And they use this for what we just showed with Stratix, I guess with Versal. They use it for time borrowing, right? So they can use this to do clock skew scheduling. Yeah?
How does Ultra handle clock gating?
The end user has to ask for it, okay? I think you basically have to say, I want a clock gate. I don't think it'll do it automatically for you. So you basically, in your design logic, you have to put a clock gate signal on your clock. Does that make sense?
Yeah, but I mean, how Ultra routes the clock signal inside the H3 if you have clock gating as well?
Well, this other signal is going to come from the regular routing, right? So like that clock gating signal. The clock gating, so Altera only does clock gating at the root of the clock network, okay? So you basically can instantiate what's called a clock control block, and it exposes some signals to do, like you can send in an enable signal, and that will be used as a clock gate. Ultrascale can also gate at the root, but it has this additional ability to gate partway through. To be honest, I haven't actually gone into Vivado to see how do you use this. We thought about doing this inside of Altera and then thought, wait a sec, how are we going to expose that to the user? Because you're gating partway through. It's kind of a mess for the CAD tool. So I guess I don't actually know exactly how this intermediate AND gate is exposed, because the challenge with it is I might have a clock that fans out to 100,000 things, and if I want to gate like 10,000, does that mean that Vivado figures out these 10,000 should be put together and I route a signal to the AND gate? I don't know, actually. I know that we thought about it at Altera and decided that was too big a mess and we didn't do it. So that's a good question. I can't fully answer it. Okay, and we already kind of went through this. The value of this clock skewing is, for example, if I had a difficult transfer from a register in this CLB to the timing path ends in this CLB, if I basically turned on the delay chain for this clock and the CLB chooses the delayed clock, it's going to make that transfer easier. These other CLBs choose the original undelayed clock. This is kind of what we already showed for the Versal example, right? And it'll have the same trade-off that we talked about before. The hold time constraints will get harder. Going from blue to red, the setup time constraints will get easier. So it gives them another tool for closing timing. And this is what Xilinx showed in the Ultrascale Plus paper. Basically, the green line is what frequency gain they get across a suite of benchmarks by doing clock skew scheduling. And basically, it's a function, again, of this is now how much margin they have on hold. Like, if they had 295 picoseconds of margin on hold, it means they can skew the clock by 295 picoseconds and not worry about hold, right? So it's like better. So they get their biggest gains when hold time is easy, less gain when it's not, and they get the biggest gains on the fastest circuits. So they get 7% overall, but they point out this is kind of helps you the most when your clock frequencies are high. So it's actually the most challenging designs that could help the most. They also compared this to using pulse latches, because pulse latches, by extending the pulse, you get a kind of an alternative form of time borrowing, and that's what they get with the red line. So they basically point out that clock skew scheduling seems to get more gains than using pulse latches with variable pulse widths, especially if you basically your hold time is a bit challenging. So they like clock skew scheduling better. Okay, so last thing on Versal clock skew. So the other thing they note in the Versal paper, so that was Ultrascale, but they adopt all those techniques in Versal, so they kind of carry them forward. In their latest chip, they point out that clock skews are increasing due to process variation. Okay, so you use those carefully built low skew networks, and you still wind up with a bunch of skew when you actually measure real chips, because they're not ideal. And the percentage of the clock period by which your clocks are skewed to different registers tends to increase with clock frequency, just because your clock period is shorter, right? So the same absolute value of skew is a larger fraction of your clock period, during which you can't really do useful work, right? So Okay, so they basically are worried about process variation increasing skew, especially on the fastest clocks. So in the Versal paper, they looked at, could they take these variable delays that they put into the last part of the clock network and use them not just to make skew on purpose, but also to remove skew on individual chips, which is a little different, right? This is now something that you're not doing it just for the average chip, you're trying to change the skew for different chips. So in Versal, what they do is the last stage of the clock network, kind of that ribbon spine part of the clock network, they call a clock region. And they built phase detectors at the boundaries between clock regions. So a little circuit that basically tries to figure out, is the clock on the left edge, is that arriving before the clock on the right or not? Okay? And they have a whole bunch of different clocks in each region, so they have to build a bunch of these phase detectors. When you configure the device, so you're programming the device, it actually has the adjacent clock regions, they run for a while, and they're checking what is my phase compared to my neighbor, and they actually self-adjust their delay chains to try to reduce the phase difference. Okay, so the clock network is basically adapting the delay to the last branches of every network. You have to do this after it's configured, because you kind of have to know which, like how are you trying to use the clock network, right? Like it's highly configurable, so you have to know how you're trying to use the clock network and which clock lines are actually carrying the same clock, right? So your line 15 in this region and your line 14 in this region, and I know you're carrying the same clock. I want to turn on the phase detector between you, see who's early, who's late, and adjust the delay chains. So this is transparent to the user. So Vivado would have presumably stored a bit of extra information in the bit stream. And then as the device is being programmed, before it says I'm done and I'm ready to be used, it basically does this deskew procedure. And Xilinx in this paper says that it can reduce the clock skew by 60% versus just using a regular non-adaptive network. And this is a cool picture from their paper that's just kind of showing the skew as this algorithm proceeds, converging to a smaller number. Yeah?
Would PLL be used to implement these phase detectors, or?
No, PLL is pretty expensive, so I assume they use something much cheaper. You can do this kind of stuff with just like counters of like, did this signal arrive before that? Like sort of one shot, this sets, this resets, and what am I seeing? Am I consistently seeing this thing's always like a 1? In which case I would say the left thing is early compared to the right, or vice versa. But yeah, PLL is really big, or pretty big. And they don't reveal that much about how these work, but they presumably have a lot of them, because they say they're in between the clock regions, and like I say, there are 10 to 100 of those per device. They probably have some muxing in front of them, because they have multiple clocks per region, so they could basically over time say, let's compare these two clock branches and try to align them. They will need some support from the CAD tool, because like I said, they need to know what clock wires are actually trying to send the same clock. Otherwise, they might be trying to align a 300 megahertz clock with a 400 megahertz clock, which is not going to work. So, but anyway, it's a pretty cool technique. Yeah? I don't know. I don't think they say in their paper. I assume it's pretty fast, though. But I guess I'll have to take a look at the paper to see. I believe it's fast because they don't make a big deal about it from an end user perspective. If you can hide it, and the configuration takes, say, 100 milliseconds for a big FPGA, which is a fairly long time in terms of clock period. So if you can do this like in let's say a millisecond, you probably can just hide it in your specs. Yeah. That's a good question. If you actually change the clocks, it would. You're right. You might have to like basically say you should readapt because I changed who's doing what clock. Clocks do make partial reconfiguration extra complicated because some of their configuration bits go outside your region. Like you saw, these H trees tend to start somewhere often in the middle of the chip, which can be outside your region. So yeah, changing what clocks go to a partial reconfiguration region is complicated. And I don't know if Xilinx actually supports that or not, but it certainly leads to extra complexity. Yeah?
A lot of the on-chip clocks are being generated by on-chip PLM.
Yeah.
They have to wait for them to lock first and then they can go out.
That's a good question. I mean, they could wait for them to lock, but they could, so they probably do that. But another way they could do it is if they can get a test clock, they don't really, the truth is they don't really care what the clock frequency is because they're just trying to adapt skew. They do need to know what lines are carrying the same clock, but that's really all they need to know. So they could actually even generate like test clocks on chip because it doesn't really matter. And like I said, the paper does not go in. I'm pretty sure they thought it was cool. They wanted to tell people about it, but they did not want to give enough information that they could immediately go implement it themselves. So I'll go read it again carefully, but I don't think they go into anything like that level of detail. So, okay, so that was it for Versal. I think I have, okay, I'm going to start multi-chip integration, but I promise I'll stop on time today. Okay, so the idea of multi-chip, and this is like a cool thing that Xilinx pioneered for the FPGA industry, and they're one of the first, maybe the first to do this in the whole semiconductor industry. So they had an idea of combining multiple dice using interposers. And they did this first in Vertex 7, and they've done it in all their high-end families since then. So the idea is instead of building one giant die, build a bunch of smaller ones, but make them appear to work just as well as one really big die. And this is often called 2.5D integration, where you build multiple chiplets and combine them with a silicon interposer. So Xilinx did this first at 28 nanometers, and at that generation they could make about a 2 million LE device, which was about double the capacity that anybody else could build in that process node. So that's one of their advantages, right? They could just build a bigger FPGA than anybody else, and there's a market for the biggest possible FPGA. There were some high-end systems and some prototyping systems that just want the biggest. The other thing they get by doing this is, this is probably a smaller gain, but in some of their parts they'll do things like, this is one chiplet, it's a big chiplet, and they'll put 3 of them together on an interposer to make you a pretty big chip, and they'll put 4 of them together to make you a really big chip. That saves them some mass costs, right? Instead of taping out 2 chips, they taped out 1 chiplet, and then they either sell you 3 or 4 of them. But they need to be combining multiple chips on a board, and Xilinx clearly likes this. They've been doing it from 28 nanometers all the way through to Versal. The way it works is they have something they call a super logic region, which is basically an FPGA. So this is a picture from Vertex 7. So they have 28 nanometer FPGAs. They put micro bumps on top of them, okay? So little solder bumps, they're smaller than what you'd use to connect to a package. And then they flip them upside down. They mount those on top of an older generation, so 65 nanometer silicon interposer. So it's again silicon technology, which gives you much denser interconnect. It's only wires, no transistors in the interposer, and it also has micro bumps. So you basically have the micro bumps connect to the micro bumps, and you get a much denser interconnect than you would through a package. So a package is usually made out of organic materials, and you can't get the same density, and to connect to a package you usually need much bigger solder bumps. And then from the package you go to actually even bigger solder bumps to connect to a circuit board. So all these things kind of at a high level look kind of similar. It's all bumps and wires, but silicon is much better at making small bumps and small wires. So you get much more density. One thing you need to have here is I do need to be able to get through this interposer. I got to get power, right? And I got to get my IOs that go to the package. So these black things are called through silicon vias. So you actually etch things all the way through the silicon and fill them with metal. They're reasonably large compared to they're much larger than a normal via. But you only need 1,000 or 2,000 of them. So those are getting you, that's your way you're connecting to the actual package. Otherwise you'd have like these 2 chips that are face-to-face mounted and there's no way to talk to them, right? So they might be doing something good, but nobody can tell. Plus no one can power them. So probably they're not doing anything good. So that's how it works. Yeah?
Another benefit I should see to this is that each chiplet can be a different process node.
Yeah.
If you didn't need certain, if you wanted certain regions to be both processed, which really go to both processes.
Yeah, that's true. And Xilinx hasn't really used that, but Altera has. So I'll show you that later, because that is another, these don't have, Xilinx does, all of them are the same. Okay, so they make identical logic regions, but you're right, you could make them different and combine them. Yeah.
This might be a little bit, it's kind of related, but
like the really big FPGAs are usually, they're used in either high-end systems or for ASIC prototyping. And there's a market for like, if you can make an FPGA that is bigger than anyone else's and you want $100,000 a chip, there is, ASIC prototyping will pay it. So they're pretty cost insensitive.
Right. So I'm thinking because I'm also taking Jason's course, and he mentioned that Synopsys has kind of like a tool that allows you to partition your circuit to fit into those FPGA prototyping devices. And that got me thinking, if how does that make sense that Synopsys, which is not an FPGA company, has a CAD tool to target FPGA products for like basic prototyping? Like that doesn't really fit.
I mean,
has their FPGAs and they make their CAD tools. Xilinx does the same.
basically Synopsys builds things on top of the FPGA CAD tools, right? So if you have an ASIC, it's always bigger than the biggest FPGA. If it's a cutting edge ASIC, which is where, so say it's cutting edge ASIC, you're NVIDIA, right? So you're making like the biggest ASIC you can make that will fundamentally always be much bigger than the biggest FPGA you can buy. So if you want to prototype that, you either do it in simulation, which is fine for blocks, but for top level, like you actually want to run a graphics driver on it, it's unbelievably slow. I mean, it's like millions of times slower than running for real. So the problem is you can't, like booting an operating system, running a graphics driver, you can't do it. So they will actually prototype on FPGAs, which are much faster, but they have to combine. They want to do a really big ASIC, they might have to combine, anywhere from 100 to 500 FPGAs. And the reason they need 100 to 500 is not just the capacity of the FPGAs, it's the IOs. Because you can't fit it all in one FPGA, so you have to cut it into multiple. As soon as you cut it into multiple FPGAs, you start going, I'm limited by my IO count. They time domain multiplex the IOs so they can try to get more signals through, but basically that's why they want the biggest FPGA. If they could get a bigger FPGA, not only does it replace two smaller ones, it removes like a cut point for IOs, which is quite beneficial to them. And what they're adding is essentially all that partitioning software, a box that combines like 100 or 500 FPGAs or whatever the latest numbers are, and tools to sort of help them extract state from the FPGA to do interactive debugging. Does that make sense?
Just buying on Xilinx FPGAs.
They don't make their own. They go off and buy like either Xilinx or Altera FPGAs, and there's kind of a, if you can make the biggest FPGA, they like you. That's what I mean. So like there's an advantage if you can make the biggest possible FPGA that you have a pretty cost-insensitive customer in like Synopsys and some of its competitors. I guess they're probably not completely cost-insensitive, but they will pay a fair amount. Yeah.
I guess this is kind of a bit related to what you do with Cerebras. Is Cerebras' idea that you have millions and millions of chips on a giant wafer? You kind of have this idea of break up the FPGA with a smaller tile, it's better computer. I guess what's the value proposition? You want to get better people to have a chip on a giant wafer.
Oh, we'll talk about that next week. How about that? Okay, so that is a good question. You can ask me after if you want. You need repairability, I guess, is the short answer. If you made an entire wafer like Cerebras does, and you said everything has to work, you might as well just burn your venture capital right now. Like, just go have a barbecue, because that's not going to happen, right? So, yeah.
For FPGAs with a processor subsystem, would you have the processor in every chiplet, then some disabled, or?
That's a good question. So I guess it depends how you do it. For Xilinx, so far at least, they've been making identical chiplets, which means they would have it on every single one. If they make different chiplets, then it wouldn't be. So I guess you don't have to do that. You just have to make another mask. Do you know what I mean? So, okay, so let's end there, and we'll see how fast I can go next week.